Okay. I think we still have some other people joining the call. I think I will start like perhaps like um, in my local time. It's 6 minutes later because I'm in the time zone, yeah, different from you guys. So it's difficult. So let's start like 6 minutes later. In the meanwhile, not sure if you have read my emails. It would be great if you have installed Docker on your PC and install the mobile app. So if you get on Discord, you will find the pinned message there, and you can find all the links you need. So we will be starting like in 5 to 6 minutes. Okay, just a second. Okay, I'm sharing my camera as well. Can you see my camera? Great. Cool. So is anyone on Discord yet? Let me check. Hi guys. So if you're on Discord, there's a few links you can find. You can find the GIS, which is the first message I pinned, um, and it will look like this. So you can download the latest simulator. You can find the Docker installation instruction if you haven't done so. So all the links you can find here. And also on the Discord, you can find the QR code to download a mobile app in which we will be using later on. So if you haven't installed stuff, you can do so now. So it is very important you have Docker installed and also download the simulator, because like it will take a while, and uh, perhaps if you do it now, it would just be fine, because like the simulator is like 200 megabyte, and the Docker installation would take a while. So um, before we start, let's do it maybe. So at least do the first two things. You can find the information on Discord. Anyone have any questions? So okay. We'll be starting in like 1 or 2 minutes. Okay. Okay, cool. So, okay, cool. So let me check something and we will be starting very, very soon. Okay, we have one more people joining in. Great. So let's get started. Okay. So thank you very much for joining. I'm Jonathan. Today we will be talking about like how to train your self-driving car. So before we start, I think I'll say this again. If you haven't downloaded these files, you may want to download it now. So while I'm speaking, you can take time to download it if you have a slow internet. And also you can check Discord what you have to do because we have a virtual race we'll be doing later today. So perhaps like half an hour later, or yeah, something like that, 45 minutes later. So get yourself like ready and we can do something fun together. So let me start this presentation. If you cannot hear me or if you have any questions, please just ask in the chat. I will be monitoring the chat. So okay, let's do it. So my name is Jonathan. So I'm the project maintainer of the open source project called Donkey Car. I'm also the founder of Robocar Store. Um, we sell Donkey Car starter kit in a website. So we also promote Donkey Car as an AI education to K-12 students. So so yeah, that is our company and our company website. So we actually design and manufacture our own version of Donkey Car. We're also active contributor to the Donkey software stack, and we have a lot of hobbyist customer coming from around the world. So people get interested in how they can train an autonomous car. So they just buy a starter kit from us, and then they assemble the car and do a lot of things they want to do or try something that like ideas they have and they just try to make the car work. So we also do some teaching in Hong Kong. Yes, I based in Hong Kong. So we introduce this donkey car thing to secondary school, like maybe K9, K10 to K12 student. So we talk about this kind, let them know how it works. So most of the slide I am going to present to you today, I use it in the daily school when I teach the student. So we also do workshops to teachers so they can try their own before they introduce it in their class. So in fact, we have also done like in 2019, when the HITB Amsterdam is happening, we have put a big track here. So we have a group of people learning how to use Donkey Kong and they race on this huge track, which is quite fun when we do it like 2 days, 2 or 3 days, I forget. But yeah, and then we race here and also introduce this donkey car to audience coming in. So it is a beautiful city and I enjoy it so much. So what we also do is like we put the track in a big shopping mall in Hong Kong and let the general public to check what this donkey car is about. So and I want to actually introduce this to you. This is there's an event called Self-Driving Global Challenge, which happened in 2019 in China. And actually, as far as I know, they want to do it every year. Because of the pandemic, they didn't do in 2020, but this is such a very interesting event. So in this event, um, there are two parts. One part is the donkey car race, and the other part is a full-size car racing. So it's not racing; it's like a kind of like a mission. Let me show you a video. Okay, so this is the full-size car. We have installed a light. They have installed a LiDAR here, and also they have a PC in the back of the car. So in this video, they are going to capture some of the data. I will show you this one. So they are trying to like capture the um, the stop sign here. So because when they see this stop sign, they actually need to stop the car. But if they do not see the stop sign, they should not stop the car. So they are doing data collection here. So when the real challenge happening, the judge or the organizer will randomly cover this sign or not cover this sign. So they need to do this, and when they stop, after they stop here, they can proceed to the next checkpoint. So it is a lot of fun if you are interested in autonomous driving. So like you can actually join this self-driving global challenge next year. I hope next year, like 2021, like in fact, they sponsor people coming to China. You don't actually have to pay for anything. They sponsor the air ticket, they sponsor the accommodation, everything. So if you're interested, let me know. And if they are going to organize it next year or anything, I will let you know. So I also actually block this in Medium. So you can check this out. I can paste the link on Discord and here. So you can read it later. So I actually blog what we are doing in this like a garage things. We have like this vehicles we can use for like install and program things inside the car, and they have all kinds of sensors, cameras, the PC here, and I have also described the challenge. You can refer to it later. Okay, great. So let's talk about what is Donkey Car. So Donkey Car is very simple. It's actually an open source driving platform. It runs on Raspberry Pi. You can also put it on Jackson Nano. It has a camera. It has Python code running on the Raspberry Pi, and also it uses TensorFlow. So by using all these, uh, you can achieve autopilot. So how does it work? All right. So on the Donkey Car we are going to sell in December, we are going to release a new version. It also comes with a controller board designed for Donkey Car, so it can support a lot of things. It has a NeoPixel, which is kind of a programmable LED light, and also IMU, and also other sensors there. So we have used this in our new release as well. And actually, because Raspberry Pi is not very powerful when running like a neural network, very heavy neural network, or even if we talk about object detection, it can't actually run it very smoothly. So we can also attach a Google Coral USB accelerator um, uh, 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 to the Raspberry Pi to accelerate the inference. So we can like doing all those kind of object detection pretty smoothly. Okay, so let's talk about how Donkey Car work. So it is a very simple three step. So we first collect the data, which is actually at this cycle today, we're going to experience it using the simulator and also the virtual Donkey Car. So we first collect the data, and then we also train the pilot, and then we test the pilot. If the pilot is not good enough, we collect data again, train our autopilot, and then we test again. Okay, so today we'll be using a mobile app, okay, and also using a virtual donkey car together with a simulator. So first, the donkey car take a picture. In a real donkey car, it will use the camera. Today, we'll be using the scene generated by the simulator. And we also get your input. So you will be driving the donkey car first to collect the data. And then in a real donkey car, they'll update the servo. For our case, it will update the simulator how much throttle and how much steering we want the car to go. And actually, the software will save that piece of images and also um, the input you're sending to the car. Okay. So we keep doing this driving inside the simulator, and we want to collect like 10 to 50K record. Okay. And by the use of like a Keras and TensorFlow stuff coding here, at the end, we can generate an output of the steering and also the throttle here. So we do some training here. And then when we do autopilot, we give an image input to the neural network. And going through all the neural network, the system will give us a throttle out and angle out. So we just test, drive, repeat, continue this loop. So at the end, we test whether the autopilot is doing good or not. Okay, so there are several kinds of machine learning. So we have supervised learning, unsupervised learning, and reinforcement learning. So in this case, since we are providing input to the image, we teach the car how to drive while the car is recording the image. We are actually tagging our driving skills or driving habit to that image. So this is supervised learning. So we will also talk about reinforcement learning later today. Okay. So the software and the community. So we have a mobile app called Donkey Car Controller. So we built this Donkey Car Controller because like to be used for this to be used in school, normal student wouldn't be like that skillful typing commands and etc and etc. So we built this mobile app, and the student can complete data collection, driving the car, check the data, they can train the model and do autopilot in one single app, which is we are going to use this app later today. Okay, we also have the documentation. If you go to like here, okay, so we go to docs.donkeycar.com. You can find all the a lot of documentation here maintained by the community. So there's a lot of useful resources here. If later on you feel interested, you can go through all the docs. Yeah. Okay. So Donkey Cars is an open source project on GitHub. As you can see, it has like it's actually one of the most popular self-driving library. We have like a 2K star, almost two. I think today we have 2K star here, and then we have like 3,000 member actively exchanging ideas on Discord. So we also have this simulator we will be using today. So we can do standard donkey car drive train test cycle. And I will show you how later. So it also support that if you're not using donkey car software, you can use other kinds of software and then join the virtual race together. So talking about virtual race, actually the community is doing a virtual race league every month. And we can do like AI versus AI. Most of the time we are doing AI versus AI. And then and we just try to see which one who is the best AI can train the best AI agent. So before we do the virtual race, I want to talk about self-driving car for a while. So when we talk about like self-driving car, we always want to introduce something realistic in the real world to the students. So we know that on the left hand side it is Tesla. On the right hand side, it is called it is developed by a company called Waymo. You may not know Waymo very well, but you must know its parents company. Its parents company is Google. So when we talk about self-driving car, we always talk about Tesla because Tesla always claim that they have like a autopilot function, right? And Waymo, we heard a little bit uh, in at least in Hong Kong, not a lot of people know Waymo. So we also talk about self-driving levels. So um, so this diagram actually describe because there when we talk about self-driving, people always talk about level 1, level 2, level 3, level 5. So I also want to introduce this concept to you. Um, so level 1, 2 is not actually like autopilot or self-driving. So you can see that both hands needs to be on the wheels. Okay. On the level 3, you can leave one hand on the wheel. On the level 4, you can leave both hands leaving the wheels. And level 5, maybe in future, you will find a car without a driving wheel. So you can check this self-driving in levels later. You can Google it, but generally you know what it means when people talk about self-driving. Okay. And there's a lot of like a sensors in a self-driving car. um, Something you may be more familiar with, like GPS, ultrasonic, something like odometry or lidar. You may heard about it because like the latest iPhone 12, it has a lidar. So we have all kinds of sensors in a self-driving car, including cameras. So for example, Tesla, they rely heavily on cameras and other sensor, ultrasonic or radar, but they do not have lidar. In in and and if you can compare Waymo is using lidar. So there's a great debate on whether self-driving car would require a lidar or not. And for your information, lidar is extremely expensive. So um, you can imagine why Tesla is not using lidar, because actually Tesla is producing a lot of car every month. Compared to Google, Google is just manufacturing like a small fleet of cars for its prototyping. So uh, in a practical term, Tesla cannot add lidar to their car because like it would be too expensive for them to do so. But for Waymo, it's okay because they're not actually mass produce their self-driving car. Okay, so this is lidar. So I would like to go through very briefly what lidar do. So you can see that in the simplest term, there's a laser beam scanning the whole area. So we can see a cylinder here, and when the laser beam scan the surroundings, it scan that, okay, there's a cylinder here that may uh, maybe in my way or something that I should take note. So in this car, we also have a lidar here. This is, if I remember correctly, it is a 16 lines lidar. So it constantly scanning its surroundings. And this is a closer look. So we can actually, when we drive through, this is pictures I take when some of the people they're driving the car. I just show you around the whole campus. We are doing the self-driving challenge. They use the lidar to produce this digital map. So um, they can scan all the surroundings and produce this digital map in order to do path planning, and also make sure the car is running on the right position, or is like driving in the right position and not crashing into a wall. So this is something that is done by by the lidar and also the software to generate it. Okay. By the way, I also want to talk about like this is uh, um, it's an estimated Tesla autopilot miles. What it means is that actually Tesla is using all the car they sell to collect driving data anonymously, and this is how many miles they have collected in 2019 and 2020. So they have they have I think they have the biggest database of real life driving miles that could help them theoretically or practically to train their autopilot system. Okay. And I also want to I also will talk about the social impact when autopilot or driving car is become like a real thing in the near future. So I always talk about this picture is that when we have real self-driving car, this guy uh, who is it's kind of a police officer is in Hong Kong. So what these guys do is to see who is doing illegal parking, and they will issue tickets to the car. So in future, actually, if everybody is using autopilot or self-driving car, imagine if you have a self-driving car, you won't be like um, parking illegally. You just tell your car to send you to your office, and then you get off the car, and the self-driving car will maybe head back home or do something else. There are some interesting things that uh, people think about. For example, is that after your self-driving car um, send you to office, probably you may not want it going back home because it will use um, some of the gas or electricity. Perhaps you will send it to a very nearby car park to park there. Even better, people suggest that if I can send my own self-driving car as a Uber to earn money while I'm working in office, it would be perfect. So this is something that like people has been suggesting when self-driving car become a reality. So we will also have some other like implication that is quite interesting. So maybe we won't be able to own our car because like Tesla would not be selling cars to us. Other self-driving car vendors or makers, they will operate their own fleet and offer us transportation services instead of selling us the car. And we actually do not have don't need car park space in buildings or on roads. And since no one is buying um, the car financing industry or the insurance industry may go away, and a lot of lawyer may lose their revenue because there's no longer a car accident or something that people will need to claim or sue each others. But on the bright side, like senior citizens, some of the senior citizens in Hong Kong, like my father, he actually need to renew their driving license every year because of the age. So in Japan, some like elderly, they lose their driving license because their physical ability they is not allowed to drive like a machinery like the car. So if we have self-driving car, their life will be greatly improved and their social life could be maintained because they can visit other people using the self-driving car. These are some of the examples that people will talk about when a self-driving car become a reality. And also, because of self-driving car is happening, there are other topics that people talk about. For example, what decision should the self-driving car make? For example, in this picture, there are one dog and one cat um, driving towards a group of human beings. So if the car drives straight forward, and then it will kill all three of these people. And if the car turn left instead and hit this speed bump or something like a concrete here, then it will kill the passenger on the car. So in case of a mechanic error or failure, what would the computer do? Would they kill the human beings on the road, or they kill the human beings or other people on the car? So there's a lot of scenario that this moral machine from MIT, that they want to crowdsource our decision and put it onto self-driving car. Okay. So, and this is a very interesting video I want to show you. It's about like Tesla. So let's pause this for a while. Let me give you some of the context what this is happening here. So we see a Tesla Model 3 here, and actually the owner is trying to test one of the feature offered by Model 3, which is called the summon function. So the summons function is used when you go to the shopping mall, because like in some country, the shopping mall is extremely big, and sometimes the car park is also very big, and you only park in the Tesla or your car in a very far away place. And Tesla has a function that you can call your car to pick you up when you have a eyesight contact with your car. So you just press the app, and the car will drive autonomously to you and to pick you up, so you don't have to carry all those heavy groceries back to where you park the car. So this guy is trying to test the summon function, but something happened. Let's see what happened. Okay. Okay, let's turn on the sound. Okay, can you guys hear the sound? I just want to make sure, because
Yes.
like, yeah, okay. So you can see that it is driving autonomously, and they're filming the thing. And note here, there's a white line here. So let's see what's happened. The white line means that the car should stop before the line. So we saw a police officer actually see this happen, and the Tesla is still moving, and the police officer asked the Tesla to stop.
All right, that's not good. The police officer just pulled over the Tesla. It ran the stop sign.
But the police officer cannot find the driver. So they have stopped the summon function, and the police officer came to check where the driver is. Okay. So it's funny because he cannot find the driver. So they're explaining to this officers that this car is running autonomously. Yeah. Okay. So actually, we won't go through all the videos here, but I just want to ask one question. Legally, so who get the tickets? Obviously, if I'm using that function, I shouldn't be the one who get the tickets, because I don't design the autonomous function. I would not anticipate that that Model 3 would not stop before the white line. So would it be Elon Musk getting the ticket or the director of AI in Tesla get the ticket. So this is something that we can discuss or even debate. So um, yes, and also like security. So there are some researchers adding like modifying this speed limit size in order to trick the car seeing this sign. When they see this sign, they may have mistaken this sign as 85 instead of 35. So imagine in a very busy town or in the area of a hospital, uh, uh, when what if people like messing around with this sign may what will happen and how we should like avoid this. Okay. Okay, so talking about like donkey car, um we also have something like uh later on today I can show you something like this is some kinds of technique we will be using. Is like it's showing a footage of we are driving in a remote control track in Hong Kong, and we are doing some kind of something called salient visualization, which tell us which pixel actually trigger the autopilot's action. Okay, and in donkey car we also have develop some kind of voice control here, then we can play. So we can talk to the car and the car can start autopilot immediately. So we can also do speed up and slow down to control the car. So this is a donkey car running on the track. Okay. We also do a stop sign recognition with donkey car using the Google Coral I just showed you. So the donkey car will stop hopefully before this stop sign because it is analyzing if there's a stop sign nearby. When we take away this stop sign, the car will continue moving. Okay. So I also want to share with you some of
Yeah,
the
sure. Just what is
video
it?
I think which is quite interesting. So this is the director of AI in Tesla. So when we just talk about stop sign we do in donkey car, you would think that this is a very easy task, but actually it may not be that easy. And let's hear why this is difficult.
It's quite difficult when you get to the long tail of it, even to create a simple detector for a stop sign. So first of all, stop signs can, of course, be in lots of varying environmental conditions. Stop signs can not just be on poles, but can just like on walls. Stop signs can be temporary and just hang out in different configurations. Stop signs can have funny lights in them, which are supposed to make it easier to see the stop sign, but for our system it's the opposite. We have to actually explicitly worry about it. Stop signs can be held by a person. That stop sign can be in an inactive state or an active state. Stop signs can be on like these cones. Stop signs can be heavily occluded in lots of ways by foliage, by size. Stop signs can be occluded by cars. Stop signs can be part of cars, and they can be part of cars in an active or inactive state again. Stops can be sort of held by a person. Stops come with lots of exotic modifiers to them. So this stop only applies except right turn. This stop says take your turn through this place. This stop is right turn, keep moving. So do not stop if you're going right. So there's a variety of modifiers, all of them we have to care about because they actually have impact on how you should drive through this defined space. And as I mentioned, everything is AI vision based at the moment. We do have maps, of course, that we build, but they're not high definition maps. But stops can be attached to gates, but they only apply when the gate is closed. When it's open, they do not apply. Stops can be in arms. These arms can lift, and then the stop sign does not apply anymore.
So I would just stop here, and you can actually realize how difficult it is if you're working on like a self-driving car. Even a stop sign, you can see that it is actually not easy to cover all the case, and in fact, in a real world case, you can see like subsite like this, and you need to figure out a way to solve all those subsite. So there's a thing called reinforcement learning as well. So in this picture, do you remember these two guys? So one of them is representing a company called DeepMind, and the AI, which is there's the AI playing chess with this like I don't know what is this English. So this is kind of like a world champion or champion or something like that. So the AlphaGo, the AI AlphaGo is playing chess with them, and he easily beat this guy and also the world champion later on. So reinforcement learning, we have heard AlphaGo, and there's something called AlphaGo Zero as well. So I would like to show you this. This pictures is saying that there's a this AI AlphaGo Zero. It in 3 days it surpassed the ability of AlphaGo, and in 21 days it it also surpassed another AlphaGo variant. So in 40 days it beat everybody in this earth, on this earth, including all the AIs. So reinforcement learning is something like about maximizing reward. So the AI is learning by himself, figuring out what is the best strategy to maximize this reward. We don't tell it how it can achieve the result. So in a layman term, it is achieved through trial and error. Of course, underlying the policy or the algorithm is much more complex, but in theory, so this is what it is doing. Okay, so in Donkey Car, we can also train a reinforcement learning agent as well. So this is uh, we have trained something like uh, a reinforcement learning agent inside the Donkey Car simulator. Uh, it is doing something very funny. If you notice the front wheel of the car, it is shaking. So, so I want to ask you, why is it shaking? So basically, we define a reward function and is trying to maximize the reward. The reason its shaking is interesting. It is closely related to the reward function. So in the reward function, we asked it to um, uh, get as close as the center with the center line as possible, but at the same time trying to extend the time it can do on the track. So by doing this reinforcement learning, the agent actually realized that by turning left and right, it can actually extend the distance it maintains on the track while it can also stay as close as the center line. So it's actually a bit scary because it find out a way that we haven't may we most of us may not have imagined of. Okay. So there are other questions as well. So supervised learning versus reinforcement learning, which one is better? Or can a reinforcement learning agent trained in a simulator runs in the real world? So we put agent training inside a simulator. They can train numerous hours inside a simulator. But how about if we put this back to our real world? Will it work as well? So this is one of the questions people is asking and also trying to make it work. Okay. So at AWS has also created, they released a card called Deep Razor that rely on reinforcement learning. If you're interested, you can check out AWS website. It is called Deep Razor. It is pretty interesting as well. So, okay, that's it for the presentation, and I want to move to like our virtual race. But let's have a break for 5 minutes. So by doing the break, I need help from you. Uh, Please refer to Please let us know if you want to participate on the race. If you want to participate on the race, please sign up for the race first. We have a Google form which is on Discord and also the chat of this Zoom meeting. So please sign up there, and we will teach you how to set up a virtual donkey car and also join the race. Okay, let's have a break. We'll come back on like 8:55 in my time zone. Okay, first sign up the form and then install stuff on your PC. If you have any questions, feel free to ask us on the chat. Okay. Great. We have 3 people signing up already. So I can see that there are 2 people uh, who is using Windows, right? So do you guys have the Docker installed already? Hi, Dillian. Thanks for joining. We are having a break now, and we will resume like on 8:55.
Sounds good. Sounds good. Sorry, I'm late.
No worry. You just about time. You can join the race.
Yeah, I was
Um,
watching. I was watching you guys on Facebook. It was awesome. Good stuff.
yeah. So, um, if you want to join the race, please sign up.
Yeah, sure,
Okay.
sure.
Sorry, I don't know how to pronounce your name, but your Docker isn't working. Okay. Um, right. I can help you later when we start train Nav Navnev, right? Okay. Cool. So take your time. We are having a break, and you can also install the Docker, the mobile app, and download the simulator. So when is the race? It is going to happen like 5 minutes later. But I will show you how first. It will take us like 20 or 25 minutes to show you how it works, and we can have like 30 minutes. You can train your car, you can run the simulator. Okay, so it would probably happen in next 5 minutes. I will show you how first. Just get yourself ready by installing the Docker, the mobile app, download the simulator, so you can start right after I tell you how to do it. Okay. So how other people have, do you have the Docker installed? Do you have the mobile app installed? Are you installing? Please, if you can tell us on Discord or Zoom. Are you guys ready? If you guys ready, we can proceed. If you need more time, let me know. Okay, great. You can't have the mobile app running today though. Okay. Um, you can still do it, but it will be a bit difficult. Is there any reason why you cannot install the mobile app? Okay. Um, don't worry. For all those technical issues where we can deal with it after like I show you how to do it. Okay. So what we will be doing today is like we'll first create a virtual donkey car using Docker and install the donkey car simulator. Um, it is very easy to install the simulator. You just download it, extract it, and then you double click it. It will run both on Mac, on Linux, or on other thing. So also we drive the donkey cart in the simulator using the mobile app. So that's why you need the mobile app, because you need to drive the car using the mobile app. And then you will collect data for training. Preferably you can collect like 10K images for training. And then you will use the mobile app to train the autopilot as well. So by using the mobile app, it means that it will send data to our training server. So it will be much quicker than you training locally, and you will get autopilot model in like 5 minutes. And then you can test the autopilot model in the simulator. And then you can send that model to me and I can get all your autopilot model and show you like how your model is doing against other participants. So, so okay, so this is what we are going to do today. So please download the app. If you can't download the app, it will not work, at least for now. Okay. You can find the QR code on the Discord pinned message as well, where I've put it there. Okay, just use your phone to scan this QR code and download the app. So also, please clone this GitHub project. It is a project developed by me, and then it will help you get installed the Donkey Car, virtual Donkey Car much easier. Okay, so if you go to Discord here, you will see that there's a GISC here. Just click this, and you can find the git clone command here. Basically, if I'm going to do the same thing here, okay. So let me go to tab, and then I just paste this here. So it will download this project onto your local PC. So what you need to do is open your local terminal. If you don't have Git installed, maybe you need to install it. After that, you just clone this. Okay, so you can see that I have this donkey car Docker. Okay, donkey car Docker here. Okay, so if you do not have Git, alternatively, you can just paste this command here, remove the Git code, just go here, and then you can download the code here by downloading the zip. Okay, so you download this project, and then after that, we can check what's inside there. So let me show you what's inside. You don't actually have to open it, but I'll show you. So this is the donkey car repository you just download, and there's a start.sh or start.bat inside the root folder here. So it may be a bit blurry, so let me make it bigger so everybody can see it. So basically, it is going to pull a Docker image here from the Docker Hub. This is an image I prepared, and then it will call Docker Compose to bring up the images, okay? And then it would run some commands that would set up, okay, sorry, it run some commands and set up the environment. So this is basically what it does. So if you're curious, we can also check what is in those Linux Docker Compose file. So basically, it runs these images and open two pods, and then mounted this my car folder to inside these images. Define there's a web controller port, which is 1887, and then that's it. So since this is a security conference, I would also go through this Docker file so that you know, yeah, what is actually inside running this image. So we actually use a Python image based image. We git clone the donkey car official repository, install some dependency here, nothing fancy, and then we install the donkey car library and also TensorFlow. And also we install some other dependency which help us generate some videos, good looking videos, and also install the donkey car simulator supporting library here. We also install this donkey car console, which help us to communicate between donkey car and the mobile app. You can check this open source repository as well. We develop it together with the mobile app. And lastly, we just run the donkey car console, which accept connections from the mobile app. So this is what this Docker files is about. So basically, after we use this start.sh, it will run a virtual donkey car in our system. So let's try it. So let me show you what would happen. So we are in the right project. So donkey car, we have like a start.sh here. So before I do, okay, I need to stop some donkey car I have previously like started. Okay. So basically I stop all the donkey car containers I run before, and right now I have nothing running. So when I start the donkey car here, I would just do a start.sh. If you are on Linux or on Mac, you can do it relatively easily, and you can see something happening on your PC after you run start.sh. If you are on Windows, it is actually the same after you install all the dependency, which is start.bat. It is also using Docker Compose and it will also start a virtual donkey car. Okay, great. So you can basically, if you have installed the dependency, you can do what I'm doing now by using start.sh or start.bat to run your donkey car locally. Let us know if you cannot do that. So after running that, you can see this is the output I just shown you. And then we can run a Docker PS to check if donkey car is running. So if you can see here, I've got one container running. The image is the donkey car here, and it is created a minute ago and is listening to these ports. And the image name is called donkey car. Okay, so let's do it now. if you have any problems, let me know. This is the first step we need to do. If you have any problem, just ask in Zoom chat or the Discord. Okay? If you can't run it or have any questions, just feel free to ask. So someone has Docker not working. Can you let me know like how it is not working? Do you have anything like, can you do a Docker PS? You can send us a screenshot on Discord and so we can help you. Just open the terminal or command prompt. Okay. So you're on Windows, right? Great. So what does it return when you do a Docker PS? For others, can you let me know how it is going? Is things moving good or smooth on your end? We have just like we have 4 people signing up. Yeah, if you have any question, you can ask us and we can help you set up the donkey car. Okay. I remember I saw this error message earlier. Let me help you. So how about others? Great. So YD does when you issue the command docker ps, can you see something like this? You should be seeing something like this. Great, great. So how about the other 2 guys? Do you have any success running the command? Cool, cool. So, right. So following. And how about Rammer? Rammer, are you here? Will you join the race? Okay. Great. So I will help you later on the Docker things. I will just show other how to advance to next steps first. So if you install the mobile app, so you will see that the mobile for the first time will ask you to accept some kind of agreement. You just click skip network setup. The app will actually start looking for the virtual donkey car. Okay, it will trying to scan the network and try to see if it can search the donkey car you just installed using Docker. Okay, so for the guys who can actually use the Docker image, can you use the mobile app to scan the network so they can find the donkey car? If you can do it, please let me know so I know you're following it. Okay, you can see the virtual donkey car by scanning the network. Okay, homework. Okay, good. Okay, so basically after you launch the app, you can actually find the donkey car, and then when you tap the car, you can actually see a dashboard like this. Okay, so there's a number of buttons that you can use here. The first one is drive. If you tap drive, don't tap it yet, but if you tap it, it will prompt whether you want to use a virtual controller or a physical virtual joystick or physical joystick. Let's not tap anything first, because at the same time we actually need to launch the simulator. So by launching the simulator, it is relatively easy. So let me show you how. So here I have got my simulator extracted here. So I have a lot of different versions, just ignored it. So I can just double click this donkey sim.x86 64, something like that. So if you cannot double click it, so I double click it, it is launching. If you cannot double click it, there's a problem that you may want to do is change mode plus X donkey sim. You need to issue this command. Okay, so how do we in on Windows, it is not necessary. It is only required in Mac or in Linux. So if you go to the simulator page, you can see that there's an instruction to install on Linux or Mac OS. You need to execute the following command. So after downloading this zip, okay, so I have it extracted here. For example, on Linux or Mac, I can open the terminal here, right click, open the terminal here, and I can just do a change mode plus X donkey sim.x80. So it will just make this executable, because previously if it is not executable, you might see something like this. Okay, let's do it. Okay, it will say it cannot display. So we actually need to change mode plus X so that this would execute. Okay, so we have successfully execute the donkey simulator. So I'm using a version 2011-13. You can also use the version just released as 2011-17. Both are fine. So right now I have the simulator running. I also have the virtual donkey car running. So I will be using the I'll be using um, the mobile app to connect in. Let me check if I can also use Zoom to share my mobile app screen. Give me a second. Okay, let me find out the Zoom link here. Okay, right. I will just paste this on our Discord so I can easily find it here. Okay, so let's try if I can actually join in using my phone. Okay, I'm joining in. Okay. Okay, I will make myself able to, uh, I will just share. Sorry, give me a second. I will allow share screen. Okay, I will stop sharing for the moment. I will try to share my screen here. So can you see my screen now? All right. It looks like it doesn't work as I expected. Sorry, guys. So don't worry. I will just launch the mobile app without you seeing it. So let's get started. So when I launch the mobile app, I actually can scan my car and then I hit drive. So when the moment you hit drive, you will see that the simulator will go into a track. So can you see that? So on the simulator, you are seeing like something like you're playing a video games, and your at the same time, your mobile app should look like this. So this is the simulator, and your mobile app should look like this. So it is like a joystick wheel that you can drive. When you drive, the simulator is also moving. So the left knob, you will be using it to control the throttle, and the right hand knob, you can control the steering. So you need to actually spend some time to practice the control. And on the right hand side, right upper corner, you can see like a recording button here. So when you press it like now, the system will start recording data. Okay. So you use the record this button to start recording, and do not stop until you have like 4,000 or 5,000 images. And use this button here, this cross, to exit the driving UI when you finish recording data. So when you finish driving, tap the exit button. It will show you a driving summary. So it shows the number of images here that you have collected, the size of the data you have collected, and also the histogram of you driving. Okay, when you finish using the mobile app to drive. So how to read the histogram? So this one, it means that user angle means that the steering distribution throughout the 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 whole driving session that you drive. And also this is the throttle, is also the distribution. Okay, good. So after we have collected data, we can finish driving, we can go to check the data. Okay, so there's a there's a terminology called a top. A top is like a logical collection of images. So for example, on this top we have like 400 images. On this top we have 300 images. So each time when you initiated a recording, then you created a top. And these are the images I previously collected. So you can use this button, you can tap here and check the images you have collected. Okay, and you can actually check the data you have collected. It can play back a video, and you can also review the images here. Okay, so after you have collected um, okay, after you have collected the data, you want to start training an autopilot model. So you tap here, the train button, and then you select the top you want to train. So basically, training is like making a brain. You provide tops, which means book for the train to learn. Okay. On the upper menu, you can tap the plus button, because in this screen, when you start training, basically you do not have any existing model on your virtual donkey car. So you will be using this button to train your first model. You choose the data you want the model to learn from, which is the top, and then you just click train, and then you submit. So minimum number of image is 2,000. If less than 2,000, the training will fail. So normally we recommend you training using 5,000 image. and the training process will happen on our server, because like if it happens on our server, it will train much faster than you training on your PC, especially if your PC do not have the GPU required. Okay, so when you submitted it, the system will show you like first the job is scheduled, and then when it start training, it will like say that the job is training. So it would like take like 5 to 10 minutes to finish each training, depending on the size of the data set. If you give us like a 20,000 images, it will train much longer than uh, 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 a training with 5,000 images. Okay. So after training, you will see that the system will give you a summary of what is trained. So this is like a normal TensorFlow chat that shows that the training data accuracy and also the validation set accuracy. So, and then you can see a button here and you can start the autopilot right away. It will approximately take 20 seconds to start the vehicle in autonomous mode. Okay. And the autopilot UI will look very similar to the driving UI, except there's a drop down here. Let me show you the next picture. So this is a picture I took earlier. So this is a screenshot. So there's a drop down menu here when you start the autopilot, and then you can check this, you can click this menu and then switch the car into autopilot. So I will show you how later. So your car would be running similar to the behavior as you drive. So in real car, there's a big emergency stop button, but it doesn't matter in simulator, right? Even if we crash, it's all right. It doesn't matter. So it's all right. And you can exit the autopilot mode by using the X button on the upper left corner. So in the simulator, we just show you here. So basically, there are 5 tracks, and we are using the generated track. Okay. So once you finish training your model, you upload it to the share drive. So Alice, who is also in this meeting, she will share the link that you can upload your model. So I will share with you how you can find your model. Okay, let me do some demo to you. Okay, so we have our simulator here, right? Okay, this is not a screenshot. This is a real car. I am using the mobile app to control it. So let's try driving slowly. So I'm using the mobile app to drive this car slowly, but I have yet started the data collection because I need to practice it more using the mobile app. And then after I am totally comfortable with this, I will start recording. Okay, so I think I'm ready now, and then I'll just use the button I just showed you to start recording. On this screen, you will not be aware that I have already started recording, but later on, let me show you where the recording is. So I have been recording like for now I have recorded like 400 images. Yes, it's pretty quick. You would not imagine that you can record it so quickly, but it is really that quick. So I canceled. I just stopped driving, and I have like a number of images, 500 something. I take this screenshot, and then let me see if I can share this to you on Discord. Okay. So I just finished it recording, and then I just upload it on Discord. You can take a look here if possible. Yeah, let me know you have checked this. So when you leave the driving screen on the mobile app, the simulator would become like empty now. And basically you can exit it, or you can just leave it there. Okay, so just now I have told you that we have collect 500 images. So where are those 500 images? So if you go back to the project that you used to start BAT and or the start SH, you can see that there's a folder here called My Car. I'm sorry, in my folder is a bit messy. There's a My Car 123. You may not have that one, don't worry. So let's focus on My Car. And under My Car, there's a folder called Data. So again, I'm going to make it larger for all of us. So just now, if you can see that on Discord, I have a tube called tube 23. So inside tube 23, we have a lot of images here. I can just randomly pick one. This is what I have recorded just now. And we have like 500 something images, right? So if you check here, we have 545. So this is the 545th images we have collected. And you can also check there's a bunches of JSON file created. On each JSON file, actually, they are recording like at that moment for this particular JPEG, what is the user angle, which is the steering, what the user using. For 0, it means that I'm running on a straight line. So for the throttle, I'm running like a 0.4, maximum is 1. So basically, I can find 500 JSON file here. Each represent the state of how I drive when that picture is taken. So basically, it's something like that. Okay, so we can find all the data we have collected here. But you don't actually have to worry about it because the mobile app is helping you to manage this data folder, as I have said. So basically, okay, you can check the data here instead of using Visual Studio Code to go into each top. Instead, just tap here and then it will show you all the images you have recorded. Okay. So after recording the images, you can train the model and then you can test autopilot. Okay. So, okay. After you have trained an autopilot model, as I said, you can use this button to start it. Okay. The mobile app will help you automatically um, download the model from our server. So if you see here, there's another folder apart from the data folder, there's a model folder. So it will save all the jobs you have submitted previously here. So we have a job 1 here, so which we can, which is something I trained earlier. So after you have trained it, most likely it will be called job underscore 1.h5. If you're happy with that, the performance of that model, you can upload it to us and we will be using that model to represent you to drive. Okay, so it is that easy. So if you have successfully installed the virtual donkey car, and you can now so you have like 30 minutes now to collect at least 5,000 images and train the model. You can do it using the app only. You don't actually need to use Visual Studio Code just like I just show you. I just show you for the sake of understanding how it works, but you can just use the mobile app and train the model and test that model by connecting to the simulator. Okay, so right now, what's the time now? So it is 9:30 now. We will be starting the race at 10. And in the meanwhile, if you have any problem, um, I will be helping you to solve the problem and hopefully get your virtual donkey car running on your PC. Okay, we have 30 minutes, and then please collect 5,000 images and train a model. Okay, if you have any question, just send the questions on Discord and I will help you. Okay. Okay. So let me try to help you to solve the Docker issue. I'm reading something now. Give me like 1 or 2 minutes. For the rest of people, can you let me know whether you have issue doing this? Because I haven't heard from you yet. Okay. Okay. Hi, Leo and L. Are you joining the race? I'm sorry, I just helped another guy to solve the problem. Are you joining the race? Do you need help?
No, sorry, I'm a bit late, so I don't think I'll be joining the race.
Okay, all right. Um, yeah, if you want to join, I can show you how. Yeah, but it's up to you. It's perfectly fine if you just want to stay with us.
Yeah, sure. I'll watch, I guess.
Okay. So because we don't have a lot of like people joining the race, so let me show you something like so what is it like when we start autopilot? So okay. So here I have a job underscore one dot h5 in my car, and like I can use this model to run an autopilot, and I will just show you how. So I have the simulator ready. Okay. And I also have the Docker running, right? So right now I can either start the autopilot using the mobile app, in which let me try this first and show you. Okay. So okay, I have only one model trained 2 weeks ago. Let's try what this is. I don't think it can work on this track, but let's try. No harm, right? So I have been loading a model. So, okay, good. So the car is almost ready. So I will switch to a autopilot mode, but most likely it won't work because I think it is not trained on this track. If this is not trained on this track, it will behave something like that and hit the cone. Okay, so let's go back and find a model that will work. So what do you mean by finding a model that will work? In fact, so I have a model here called Jonathan, so which is something I trained earlier. Alice has also trained another model. So basically, I just copy this into here. Then I will have a new model in my virtual donkey car. And I can start the autopilot again by using this model. Let's see whether it will become better. Okay. So the car is initializing. And let me choose the autopilot mode. So you can see that this car is on the autopilot mode. Okay. And it is actually now running autonomously. So because I am starting this on the app and you cannot see my mobile phone, so it is a bit like confusing, like what we have done in is it just happened like magic. So I would just quit this autopilot and let you know how I would do it by using commands. So I quit this first, and then I go back here and start manually. So okay, so here we have my car here. Okay, let's check. Inside my car, I have a model directory. And then we have this Jonathan.h5, which is a model I trained it earlier today. So in order to run this, excuse me. So let me get, let me get the right command. So basically what I need to do is to run a command inside the Docker. I need to modify a bit and ask it to use Jonathan.h5. Let's see if it works. So by executing this command, the Docker will try to find, okay, it is there already. Okay, we have a bunches of like things here running. So, okay, you can see that we have like an autopilot running here. So let's go back to this command and let the car just drive. So we ask the Docker to execute on this container, this command. This command means you use Python, we call manage, call file, call manage the py, and then ask it to drive. And then we're using the model called model/jonathan.h5. So it will load this model and start the car automatically in the simulator. Okay. So if we hit Control C here, the process will be terminated and the car will go away. So it's just like this. All right. Obviously, I'm wrong. I need to also kill the process as well. Let me just stop the race. Okay. I just killed that process and it is done. Right. If I put a flag called interactive, I think here I can Control C the donkey car and terminate the process. So I reload that model. With this model, I specify Jonathan.h5, it will run automatically. So because I know that, so let's cancel this car. Okay, it go away now. So let's see what other models are available inside my car. So we have this job1.h5. So actually we can try to use this job1.h5 and see if it crashed. Normally it should crash because this is a model we just have seen that it's not working so well. We're just trying to verify that this command will load another model. Okay, here we go. So let's see. So it should not work that well. Yes. So it will crash. So because we are loading another model that wouldn't work very well on this track. So we just cancel it. And then going back to use the Jonathan.h5 model, it should be okay to run this track. And because we have a model that runs pretty well on this track, we can actually even create multiple cars using the same model, but on different donkey container. Because right now we don't have anyone else asking me questions. So let me show you this. Okay, I just stopped this Docker container. Okay, so right now we have no Docker container running. So I have another script here called multiplayer, which will create like whatever numbers of razor I want. So I just type, perhaps maybe I should try 4. I have never tried 4. So let's do it. So you can see that it is creating multiple donkey card container here. Great. So let's check. So we have actually 4 donkey card container running simultaneously. By running the container, it doesn't mean that it will appear on the track, but it means that it will be ready if we tell it to do so. So I also have this like start NPC stuff in my local repository. We can check what it is before we run it. So we want 3 NPC. NPC means like a computer, and we can start like this number of car simultaneously. Let's see, we have a job underscore 4 here. Let me try to copy this job underscore 4 into each car so that it will learn how to, it has the model to run. Okay, give me a second. Let me demo this to you. Okay, I will need to copy and paste this too. Okay, no. So I have a car for here, models. Okay, I'm not allowed. Okay, don't worry. I will just start 2 car. Perhaps 3 cars, why not? And starting from the first car. Cool. Okay. So when I do this, let's try if it works. Starting first car, starting second car, starting the third car. Right. So we can see that we have like razor 1, 2, 3 ready, and each of them will start running on the same model. Can you see that, Leo? Because like,
Yeah.
cool. So each of them is running separately, but using the same model. Okay. So basically we created 3 NPC racing each other, but since they're using the same model, basically they aren't able to like overtake the other car. Okay. So I have actually trained an agent that race with this 3 slower agent and practice how to overtake them. So let me show you. Let's see if I can show you that. I see that there's another participant coming back. Have you solved your Docker problem yet? Or you need more time? Okay, I'll just give you more time. Okay, so let's
Just a question.
yes, please.
So since they're running on the same model, that means they're running the exact same race, or are they running different races?
So they're all connected to the same simulator. In fact, each model will see other 2 car as well. So they're running on the same track. Just that, and you can think that they are running on the same brain as well. But just like each brain may react to different scenario, because there is always some kind of physics that is creating some kind of a bit different, and then their reaction will be a bit different. So they are not running identically, but they are running nearly identically. If you are checking the race line here, I think racer 1 is the first guy. So you can see that Racer 2 is actually running on in a very similar race line as Racer 1. So Racer 1 keep the left link here, and you can see that Racer 2 is also keeping the left link here. Racer 3 following, and also he want to use the left link and make the turn. So you can see that they are following a very similar path, although sometimes it would be a bit different, but they're using the same model trained using the same set of data set. If we use another model to race with them, the result would be very different. And I can show you.
Okay. Thanks.
Okay, good. So let's try, right? When the other participant is still working on how to make things work on their PC. So I just kill everybody like here. And then I have to change something here. I just want to NPC. Okay, starting from like 2. Okay. Okay. So if I do that and start again, sorry, my bad. So I should be able to see like 2 NPC with the same model joining the race. Okay, Racer 2 and Racer 3. So in this moment, let's try to introduce another PC, and I mean like another car which runs a different model. So let's see what models is available under my car one. So I have previously trained something called job_5. Let's use job_5 to race with these guys. Okay, so how do I do that? Basically, what I need to do is just this. Okay. So we can see Racer 1 joining in soon with a faster model. Hopefully it wouldn't crash. If it crash, I will have to save him. Okay, don't crash, please. Oh no, oh no. Okay, it is running okay now. So Racer 1 is obviously running faster and a more reckless driver, as you can see. So it's trying to trace Racer 2 and Racer 3. Racer 2 and Racer 3 is kind of like a safety car. So Racer 1, he learned my bad habit of running, like uh, out of the track, but it is running much faster, as you can see. So same thing. Is it smooth when you are watching this, or this is a bit laggy? Okay.
For me, it's quite laggy,
Okay.
but I can see what's happening, so it's fine.
Okay, so we can, unfortunately, Razer 1 has crashed. Let us save it using the mobile app. So at this point, I can even control it, connect it using the mobile app, and like I can ask it to restart again, like using this model. And let's see if it can overtake Razer 2 and Razer 3. So I am okay. Accidentally, I start another Razer 1. Okay, I need to stop it first. So okay. Oops, too bad. Razer 1 is gone offline. Let's try it do it again. Okay. Let's see if Razor 1 can come back here and then race with like Razor 2 and Razor 3. Okay, it's back here now. Okay. Oops. So let me give it a little bit help, because like when you're doing like autopilot, you actually can override it using some kind of user control and then start the autopilot again. Again, it is running a bit like off the track, trying to. Sorry, discard. So let's see if Razor 1 could overtake Razor 2 and Razor 3. I've trained Razor 1 being able to overtake Razor 2 and Razor 3 without crashing into it, but it it does not always do it successfully. Obviously, not now. Okay. Oh, too bad. So it pushed Razor 3 out of the track and itself crashed into the cones. But that's the idea. So you can actually create a faster agent and then race with another slower agent. I've already again rescued Razor 1. And it is taking the corner too aggressively. I did not train it too well, obviously. But that's the idea. Yeah. Okay. So let's see. So let us stop the race. Okay. So is anyone going to race with us? If not, we will end this session soon. Okay. Let me check with. Okay, maybe let's stop here first, and if we have other chance of like organizing a race, maybe we can race next time. So thank you everybody for joining this session.
Thank you.
Thank you.
Um,
So we'll give it a bit of time. We'll see if people are coming in. You want to give it one more minute, Atit? I think 1 past the hour, so everybody can join from other talks.
Yes, it's fine.
Yeah.
Let everyone join.
Okay. Good day, everybody. Welcome. Welcome to the CyberWeek workshop session on signal processing with GNU Radio and SDRs by Atit Kumar. My name is Sjoerd, and I'll be the support person for this session. And just ping me anytime if you need any help. We would like for everybody to mute their mics during this session, so please do so Atit can show his presentation without any disturbance. It would be nice if you could save your questions until the end of the workshop, and at that time you can use your microphone or the chat to say to talk about your questions. We would like it if you turn on your webcam as well, so we can see who's talking to us. But again, that's optional, so please don't feel obliged to do so. That's it for now. The floor is all yours, Atit. Enjoy.
Thank you. Hello, everyone, and welcome to this signal processing lab with GNU Radio and software-defined radios. If some of you have attended this same lab in the HITB Singapore during the month of July this year, but if you missed, then this time you will be learning those concepts in this lab, and also there are some new interesting demonstration I have for you on GNU Radio and software-defined radios. So let me just share my screen. All right, we are good to go. Okay, so a little bit about me, those who don't know, who am I? So my name is Atit Kumar. I'm a senior security researcher in Zenith Labs. So it's a part of Digital 14 based in Abu Dhabi. And this company is involved in various kind of security research, whether it's related to hardware, it's related to general cyber security, it's related to signals or softwares. So, and I am known as the signals guy in this lab. So basically, I'm an electronics and communication engineer by qualification. And I have also worked for around 3 years as a research fellow in DRDO. So DRDO is the Defense Research and Development Organization in India. And for those who are not familiar, with this. It is analogous to the Department of Defense in United States. These are my Twitter and my Gmail ID. You can note it down, and later also you can communicate if you have any questions at the end of this conference. So we will be covering our workshop in 4 different parts. So first we'll be looking at some basics of electromagnetics and radio frequencies, then some important signal processing terms and concepts, which one must know to start working in this domain. And we will see practical GNU radio examples and do some hands-on to learn more about GNU radio software tool. Some of you are already familiar with this tool, but some people are very new. I'll be telling you some techniques and some important concepts which may come handy while you are doing your signal analysis using GNU radio software and other software-defined radios. At the end, we will see how to start the radio frequency research using a simple software-defined radio hardware and some other tools. All right, so let's begin with the electromagnetic and radio frequencies. So if you all remember this guy, Nikola Tesla, he said that if you want to find secrets of the universe, think in terms of energy, frequency, and vibration, which is very true. Because you see, all the space discoveries which we have done till date are related to the electromagnetic spectrum and the frequency and the vibration. That's how we actually understand this universe. That's how we understand our nature. That's how we understand what we do on this planet. That's how we understand this anything which exists as a matter in this universe. So interesting part that we all are very enthusiastic about the radio frequencies. To get to know about the radio frequencies, we need to first learn about the electromagnetic spectrum. So this is what we are surrounded by all the time, every time, even while we are attending this presentation. We are surrounded by so many electromagnetic waves around our atmosphere. So when you think of, let's say, light, you probably think of what your eyes can see. But there is more than what our eyes can see. So the visible light is one thing. There is also a spectrum of light waves which is invisible to us. We know it as a light only, like infrared and the X-rays. But the electromagnetic spectrum is the term used by the scientists and the researchers to describe the entire range of light that exists. So from radio waves to gamma rays, most of the light in this universe is in fact invisible to us. So we can only see a very little part of this electromagnetic spectrum, which is shown by this 7 colors here in the visible part of the spectrum. If you can see on your screen, there is a picture of a light bulb here. So this is the part, this is a small part of electromagnetic spectrum which is visible to us. The other part of the electromagnetic spectrum is not visible to us, but it is always existing. Now the electromagnetic waves which our eyes can detect, that is the visible light, they oscillate between like 400 and 790 terahertz. That's several hundred trillion times a second. So the wavelengths are roughly the size of like 390 to 750 nanometers. It's in the scale of nanometers. And our brain interprets the various wavelengths of light as different colors. So red is the longest wavelength and the violet is the shortest wavelength. So these are the two ends of the Vibgyor spectrum, visible spectrum of the light. When we pass the sunlight through the prism, you might have like studied this experiment in your high school, that when you pass a sunlight through the prism, it actually shows you all the components of the light from which it is composed of. So it shows you all these visible spectrum colors. Now, when we talk about the radio waves, so these are basically just the electromagnetic waves with the wavelength longer than infrared. So just like the other waves, the enormous range of light spectrum is like not visible to us, but existing in some or other wavelengths. So 30 hertz to 300 gigahertz is the range of the electromagnetic spectrum through which we know the radio waves. This is the extent of radio waves in the electromagnetic spectrum. And we can define radio waves in terms of either frequency or wavelength interchangeably. So sometimes we talk about frequency when we discuss the radio waves. We talk in terms of hertz, gigahertz, terahertz, and sometimes we just talk in terms of the distance dimensions like meters or centimeters or millimeters. So when we talk about the distance dimensions, it comes under the wavelength. And when we talk about hertz, gigahertz, it is known by the frequency characteristics. So we can use both of these interchangeably. Then a very important thing, those who don't know actually what electromagnetic waves are. So any kind of waves, as the name suggests, electromagnetic waves. So it is basically composed of the electric and the magnetic part. So whenever there is accelerating electric charges, they oscillate between the electric and magnetic field, and that's how we get these electromagnetic waves in our atmosphere. So space also generates a lot of radio waves. That's why we are able to discover these distance stars and some galaxies which are like millions of light years away from our planet and not part of our solar system. Some planets, some black holes, various things in the space we discover using the radio waves. Usually the scientists use the radio telescopes to see these distant objects in the space, sometimes to discover even a cloud of CO2 gas inside the in the space. We actually use the radio waves. So radio waves are electromagnetic waves too. So don't get confused by these two terms. So if radio waves and electromagnetic waves both are interchangeably can be used, that's just a part of electromagnetic spectrum. All right. So when we talk about the basic RF communication system, that's how these in these three categories all type of communication systems work. So when we talk about the simplex communication, it is basically the one-way communication. For example, the FM broadcast, radio broadcast, or the television broadcast. So usually it is only one way of communication. A signal is sent through a transmitter and it is being received by only a single receiver, and the receiver is not communicating back to the transmitter. So when we talk about the FM radio broadcast and the TV broadcast, so there is a transmitter which is broadcasting this signal into the air, and there are a lot of receivers which are receiving this signal. But these receivers are not communicating back towards the transmitter. So this is the simplex way of communication system. Then we have half duplex, where at a time only one body is transmitting or receiving. So if transmitter is active, it will be transmitting the signal to the receiver will receive. Then in the second part of the communication, this receiver will become the transmitter and send the signal towards the other device, and the other device will act as a receiver and receive the communication. So this half duplex communication, it basically have these two parts. So one at one time only one device is communicating to the other. Then in modern day communication, just like our mobile devices, we have full duplex communication, where at single point of time both of the devices can talk to each other. So on your mobile phone, when you are talking to someone, you can also like your speech signal is simultaneously transmitted from your phone to the other mobile device while the other person is speaking to you. So this is the full duplex communication. So in general, in wireless communication, in the modern day devices, we usually have these type of full duplex communications. So this is like a little bit complex to analyze the communication, the RF communication between these devices than compared to the simplex devices or the half duplex devices. One example of half duplex devices is the walkie-talkie, where at a time only one person, he presses a button on his device and he speaks, and then he waits for the other person to speak. If we talk about a general block diagram of wireless communication, so these are the basic components which a wireless communication system will consist. So the first part is the signal input. And for signal input, we usually have two different types of signals. So first is the baseband signal, which is the information signal or the message signal we have. So this is the actual message signal which we want to communicate to the other end, wired or wirelessly in both cases. This signal is usually a low frequency signal, just like I'm talking to you right now. So the speech signal is a low frequency signal, and it cannot travel a longer distance by itself. So we have to modulate this low frequency signal on top of a carrier signal, which is usually a high frequency signal. So this carrier signal will take this information signal to a longer distance throughout this communication system. But to achieve this a combination of low frequency and high frequency signal, there is a term called modulation. So we use a modulator. So what this modulator does is it changes the properties of the carrier in accordance with some property of the low frequency message signal. So when we talk about the amplitude, so this amplitude of the carrier signal will be transformed according to the changes in the amplitude in the low frequency message signal. So that's how we get the amplitude modulated signal. And now we have to transmit this signal through a transmitter antenna. But before that, we usually amplify the power of this signal, because in order to for this signal to travel longer distances, the power should be sufficient enough that if the receiver receives this signal and try to recover the original message signal from this received power, it should be able to faithfully recover the original message signal out of it, because the channel is always surrounded by a lot of noise. So there is a lot of interference from other electromagnetic spectrum, as well as inside the same frequency band in which we are operating. There are a lot of other communication going on. Also, there are some noises induced by the electronic systems in the communication devices. So at the end of transmitter as well as at the end of the receiver, on both sides, the electronic hardware will also induce some noise into the signal. And there are a lot of RF components working inside these devices, which can induce some other type of RF noises to the signal. So that may basically hamper the quality of the signal. It can distort it even. And if the noise is very high, then on the receiver side, we will not be able to actually listen to anything. Similarly, on the receiving end, we use a receiving antenna. So the transmitting antenna and the receiving antenna should be should take care of the polarization which we want to use during this communication. So polarization is one important concept when we talk about the electromagnetic wave propagation and the antennas, because it depends on the polarization that whether the transmitted signal will be faithfully received on the receiver antenna or not. So there are different type of polarization: linear polarization, circular polarization, and cross polarization. So we usually, in most simple systems, we use the linear polarization, but circular polarization plays important role when we talk about the long distance communication. Also, the size of antenna depends on the frequency and the wavelength we want to use. So antenna, studying the properties and the design of antenna is one important part when we talk about the communication systems. Inside your mobile phones, you might have observed that in the older mobile phones, we used to have these retractable antennas, which were coming out like a whip from the mobile device, and these devices used to be very heavy. But nowadays, everything is hidden inside the mobile device casing itself. So these antennas have become really small and still powerful. So antenna study is another important part. Okay, coming back to the wireless communication system. So on the receiving side, we just use the inverse process of of what we used in the transmitter side. So we usually use the inverse process for demodulate the signal. So it depends on what type of modulation we have used in the transmitter side. And after the demodulation, we usually connect it to some output transducer. So it can be a power amplifier connected to a speaker. So you may want to like listen to some music which you are receiving, like your FM radio receiver, or you may want to pass this signal to further signal processing module where you want to maybe do some sort of digital signal processing to extract out more useful information for your own purpose. So modulation is basically the process in which the modulator changes some attributes of the carrier signal which are proportional to the message signal. So this equation you are right now having on your screen is the equation of the carrier signal. Similar to this, the equation of your message signal can be, but message signal is more varying between the time and the frequency, because it's not a simple type of signal which is having only one particular characteristics. Message signals are more complex, just like the speech signal. It will be transforming in the time continuously. So this is how a carrier signal looks like. So the first part is amplitude, and this part in the braces is the frequency and the phase part. Phase is very important when we want to receive the signal, because if there are phase delay from the signal which we are receiving, like let's say this, we are receiving multiple copies of a single signal and at different point of time. So we need to take care of all the delays between these receptions, so that these different signals, which are actually only part of one signal but coming at different point of time, they should not actually cancel out, or they should not appear as a different signal to the receiver. So that's another important concept here. But coming back to the modulation, we have two type of modulation: analog modulation and digital modulation. So when we talk about the analog modulation, it is basically when we are using the properties of when we are working with the analog type of signals, just like the speech signals, or when we are talking about the radio signals in the air, when we talk about the wireless communication in general. So these are type of analog signals. So analog is basically which you can directly represent in continuous time. When we come back to the digital modulation, so in digital modulation, it is similar to the analog modulation, but rather than being able to continuously change the amplitude or frequency or the phase of the carrier, there are only like discrete values of these attributes that correspond to the digital codes. So we usually convert the analog signal into the digital domain, and then we work on the digital domain, whether it is frequency modulation or the phase modulation. And the digital modulation schemes are totally different from the analog modulation schemes. Let me just walk you through some basic modulation principles. So when we talk about the amplitude modulation, as I mentioned, that the amplitude of the carrier will vary in accordance to the message signal. And when we talk about the frequency modulation, similar thing will happen to the frequency of the carrier. And when we talk about the phase modulation, the similar thing will happen with the phase of the carrier. So it is basically changing in accordance with the message signal. These are the three equations of carrier and the message signal and the modulated output. So this modulated output you are seeing here is the general output of the analog modulation, but there is a huge derivation of this output signal when it's come to the frequency and the phase modulation. So amplitude modulation is the most simplest form of modulation one can have in the analog modulation. Now let's talk about some basic digital modulation schemes. So you might have heard of this on and off keying or the amplitude shift keying very often. So this is the very simplistic form of digital modulation scheme, where we represent the high amplitude as the 1 and the low amplitude as the 0. So the carrier properties, the properties of the carrier, which is here we are changing the amplitude in accordance with the shift in the amplitude of the message signal. but we are actually representing it as a stream of 1 and zeros. So that's how we are converting the analog information into the digital information for it to be processed inside our computers or laptops, because the machine, they only understand the digital form of signal. So it is always the case that we have um, to convert down this analog input which we are capturing from the environment to a more machine understandable form, which is basically the bits and ones and zeros. This is how a frequency shift keying will look like. So the high frequency part will look like 1, will be denoted by 1, and the low frequency part will be denoted by the 0. So the shift in the frequency is actually giving us the information whether it is a 1 or it is a 0. Then this information will again be converted through some digital signal processing back to its original message. So these ones and zeros will again be converted to the useful information which will be representing your message signal. And this is how the phase shift keying looks like. So whenever there is a phase change, it will the information will be changed from 1 to 0. So as you can see that in the first wave here, after the 1 is finishing, you can see the first peak, the short peak here. So here the phase of the signal is actually changing, and because this is the totally opposite phase of what was the previous signal, so we have denoted it as to be the 0. So that's how we differentiate between we can use this phase shift as to represent our information in 1 and zeros. All right, now let's learn some important digital signal processing concepts which may come handy when you are actually working with the hardware and the software defined radios. So first thing, a very important question which people usually ask, that when we are analyzing a signal in a frequency domain and when we are analyzing a signal in time domain, what is the significant difference here? So let me just show you through some diagrams here. So what you see on the screen, on the first waveform, you can see there is a signal which frequency is 6 hertz and the amplitude is 5 peak to peak. So this signal is being represented in the time domain. So this is a simple sine wave of 6 hertz and 5-volt amplitude, and represented in the time domain. You can see on the y-axis is the amplitude and the x-axis is representing the time in seconds. Now this is only one single waveform. So when we look into the time domain signal, we can easily identify the frequency. We can easily calculate the frequency and other parameters of the signals, whether it is amplitude or it is the time period. If we convert it down to the frequency domain, which is the lower part of this diagram here, you can see there is only one peak, which is at 6 hertz on the frequency axis. So the amplitude of this peak is still 5, but there is only one peak. So this peak in the frequency domain is representing actually this frequency, because right now we are looking at only one frequency, which is 6 hertz. But what will happen when we have multiple frequencies together? So the diagram will somewhat look like this. So here you can see the pink and the blue and the black color waveforms. These are 3 different frequencies put together on the same time axis. So this will become more complicated to actually identify and the different frequencies which are displayed here in the time domain. But what will happen when we represent these frequencies into the frequency domain? So now you can see in the frequency domain, the lower diagram, you can see the pink waveform, which is having frequency of f, is separate from the frequency 3 times f and the 9 times f. So here in this lower diagram in the frequency domain, we can easily see 3 different frequencies. So it is very much, we are able to distinguish between the different frequencies. So in general, in the nature, this signal we have or we capture will contain a lot of frequency components. So it is very difficult to actually process the signal using the time domain analysis, because we have to identify actually which frequency we want to analyze, and we have to cancel, or we have to like reject all the other frequencies which are useless for our purpose. So in that purpose, the frequency domain analysis is very important. Another important concept when we work with the signals is the sampling. So it can be any kind of signal, but sampling is very important when we are converting the signal from analog domain to the discrete or digital domain. So you might have heard of these devices called analog to digital converters or digital to analog converters. So these type of devices actually sit in the front end of your transmitter or the receiver. So when you receive a signal from the atmosphere through the antenna, the original form of this signal is analog. So this is basically a radio frequency or oscillating waveform, which is received by the front end of your device. But in order to process it into the electronic hardware of your device, of your receiver, we need to convert it down to discrete domain or the digital domain, so that this information can be processed digitally inside the receiver hardware. So to convert this analog to the discrete or digital domain, the first process is the sampling. So you can see here these lines which are having this dot, the big dot on the top. So this represents the samples which are taken throughout this time period of this waveform. So you can see that each sample is representing a discrete value here, not like the continuous waveform where there can be infinite different values between two particular points on the waveform. So in order to save this type of processing time, we have to convert down these to simple samples. So what we do is we take these samples at different points, different instances, and these samples should be sufficient enough to actually give us the sufficient information which is required to faithfully recover this signal on the other end. So these samples are actually representing the sufficient information which we need. If we reduce the samples, it may happen that we miss out so much of information that when we do our signal processing and try to recover the original message signal, there will be a lot of information which is lost. So this will not be a faithful communication at all. So sampling rate basically is defined as the number of samples per second. And this sampling rate term is very important for the digital signal processing or any kind of signal processing we do, whether it is in software or in hardware. We'll see this sampling process in the practical demonstration. So for now, you just understand that this is to convert the signal from analog to discrete domain or continuous time domain to discrete time domain. There is another important concept which is called decimation. So when we are sampling the signal and we are converting it from analog to digital, or we are converting it from continuous to discrete time, there is a loss of information there. So to fulfill this loss of information, we actually use the process of decimation and the interpolation. I'll come back to the interpolation later. So first understand what's the decimation process is. So decimation is basically known as the downsampling. So it is basically taking as much sample as required to process the signal and actually reducing the original sampling rate. So let's say if we have sampled a signal at 10 megahertz at 10 megasamples, and now for our signal processing module or our signal processing device, we cannot afford to process this high sample rate. So what we need to do is we need to reduce this sample rate further. So this original sample rate is coming from the analog to digital converter, which is sitting at the RF front end of the device. But inside the receiver processing hardware, we will use a decimation process which will reduce further this sampling rate, and it will convert down this sampling rate to a lower value so that it is it is easier to process. It also saves the cost on processing because to design electronic hardware which can process the high sampling rate, the cost also increases. One important thing to note here is the decimation process is simply the ratio of the decimation factor is simply the ratio of input rate to the output rate. So it usually comes out to be an integer value. So this factor should not be a fractional value. It should be an integer value for our device, for our signal processing to work. Similar thing happens to the interpolation, but here this is actually to recover all the lost samples which we have lost in the process of sampling and the decimation part. So interpolation is the opposite of the decimation, where we are actually introducing more samples, or we are stuffing more samples into the signal to recover what we lost in the process of decimation and in process of original sampling. So sometimes we insert the zero value samples between the original samples to actually increase the sampling rate back to the original, or sometimes we stuff this gaps between the samples using ones as well. So usually zero stuffing is more popular, and this is also called as upsampling because we are actually increasing the sampling rate of the output of the system. So during the decimation process, we were actually decreasing the sampling rate of the system at the input side, but interpolation is increasing the sampling rate of the output side of the system. Now interpolation also, because it should be an integer, and it is defined by the output rate over the input rate. I think it's time to take some break, and then we will switch to the live demonstration. So you guys can have a 2 or 3 minutes break, and then we'll join back again. Meanwhile, I can answer some questions on the chat.
So if there are any questions, you can unmute or write them in the chat.
Yes, some of you might be very new to electromagnetic or radio frequencies. So if you guys have any kind of questions, whatever we have discussed so far, you can ask. Whether you can use your mic to ask the question, or you can write it down in the chat box. Someone has asked that will it be viable to try and follow along with the demonstration. So I'll be very slow while giving the live demonstration so that you guys can follow. And I have sent some setup steps already to some of the participants. So I received a list of participants earlier yesterday, and I sent a procedure to how to set up your computers for this demonstration, for this workshop. But anyways, if you will face any problem during this workshop, the steps are very simple, and you can like follow up easily because anything which I am demonstrating here is open source, and it's available online. There is a lot of guidance available online, so it will not be a problem.
What's your question, dark web?
Okay, so the question is where this type of sampling and recovery of signaling happens in the modern time because latest technological devices are more complicated and signals cannot be recovered easily. Yes, I agree that the modern day devices are very complicated. So if I take the example of our smartphone, it's not just a simple device. It's doing a lot which we cannot like imagine if we are not aware about the technology which is implemented in this small form factor. It's even sometimes doing much more processing than our regular laptops or computers. So when we talk about sampling in general, it is basically um, okay, I should give an example of statistics here. So let's say that you want to organize a survey in a city. You cannot, it will not be very feasible to go to each of the person and then take the feedback for the survey. So what we do, we take a sample which can faithfully represent the complete population there, and then we do our survey on this particular sample only. So similar thing which we do in the signals part. So for this sampling, we take only few samples which are sufficient enough to represent the information. So we are not taking the whole signal, uh, which is the continuous time signal, because that's impractical. Because at any between any two given instances of time, there can be infinite different points which you can define on that waveform of the signal. So if I talk about like practicality of this type of sampling and the recovery of signal, it happens everywhere where these radio frequency devices are working. For simple example, if you are aware of an equipment called oscilloscope, you guys have, if you are an engineer, you might have seen one in your university in the laboratory. So these oscilloscopes, when we connect the cable for the input to the oscilloscope, so the port where we connect this cable is actually the front end of that equipment. So this front end device is nothing but analog to digital converter. That is the actual electronic hardware where this sampling is happening. So when you give the input to the oscilloscope, it actually takes the sampling first. So it converts your analog input signal to the digital signal, and then it feeds to the further electronic components of the oscilloscope, and then you are able to eventually see the waveform of the signal on the oscilloscope screen. I think that if I have understood your question correctly, then this can be the answer of your question. All right. Any further questions? So I'll start in one minute. Okay, let's start with the second part now. I hope you are all able to see the screen. Okay. So GNU radio. Okay, some of you might have heard the term before. GNU radio is a free and open source software tool which we use for building up the signal processing modules. We can also use the radio hardware with the same software tool. So it is online available. You can download the software and you can build it in the Linux system or the Windows system, and you will have a window where you can put different signal processing modules, and then you can create a whole flow chart for your signal processing. I'll show in a while how to do that. So this signal processing software tool, there are a lot of signal processing software tool actually, but GNU Radio is very handy to build applications, starting from a very simple application to visualize a single waveform having a single frequency, or even to build some complex type of communication system modules, or some complex type of signal processing module. Let's say you want to process or decode FM signal using a GNU radio module. So you can do that, and you need to have a software-defined radio hardware which you will connect, and then you can start receiving the FM radio signal and listen to the FM radio signal on your computer or your laptop as well. So let's see the practical demonstration of GNU radio. All right, so when you open the GNU Radio companion tool, you will be having a window like this. So right now I'm using a Linux system. You can also download and install the same software on Windows as well. There is a very good installation guide given on the GNU Radio website. So if you go there, you can find different process for Ubuntu, for Kali Linux, for Windows, and for Mac OS as well. So you will be having a window like this. So this whole white blank space is your workspace, and on the right side you have a search tab here where you can type any name of any module. Let's say if I type about filters, then I can see different type of filters here. So you can type and search which type of signal processing module you want to use. Also, you can drop down into each of the categories and you can select what type of signal processing module you want to use. And there are a lot of signal processing modules already available in this software tool. One important thing that you can also build your own signal processing module and add it to the GNU Radio, because this GNU Radio in the backend is it writes a Python file for whatever you will make here in this white workspace. So it will write a Python program for this, and also you can use if you are a good Python programmer or C++ programmer, you can use your programming skills to design new signal processing software, and you can directly add them to this software tool. Okay, so there are some important things which we need to know if you are very new to the GNU Radio software. So whatever the module you will be using, you need to understand what this module does. So let's say I have selected a variable here. I need to understand what my signal processing module should be doing. So you should have a clear picture in your mind what you are going to do. So let's say right now I am trying to show you a simple signal, and I am using a block which may come handy if I want to define some parameter. So just like we define some parameters in the programming C++ or Python, we use variables there. So right now I have taken a variable block here. If I double click on this block, I can give a name to this block. Let's say I give the name to this frequency, FREQ, and I can set a default value. So let's say I take the value 10 kilohertz. So for 10 kilohertz, I can write 4 zeros, which is 10,000, or I can use the notation 10 e raised to power 3, whichever suits you well, because if you are taking for higher frequencies, then it's better to write in this scientific notation here. But please note that you cannot write, if I want to write 10 kilohertz, I cannot write 10K or something. It will be not a valid input here, because as I mentioned that in the backend, it is actually generating a Python script. So the variable name or the values which we will use throughout the flowchart should be an acceptable input to the Python program as well. So we can use either zeros or this notation. So you see here it is showing the 10K on this block. And now because I want to use a signal, I want to see a signal waveform, so I will use a signal source. So this is basically a synthesizing block. So this signal source will synthesize a signal for me in the software. So I don't need to actually have a separate signal generator, but I can use this software tool GNU Radio to generate a signal just using my laptop. So now I will change some parameters here. So because I want my frequency to be variable, I don't want to change the frequency here every time. I will just use the variable which I had taken earlier, and I'll mention the variable here. The type of waveform you can select from sine, cosine, square, triangle, sawtooth, anything. And the sampling rate, you can give your own value of the sampling rate. Let's say I give 1 kilo for the sampling rate, or you can use the variable of sampling rate. So when you actually open the GNU Radio companion tool, you see these two blocks already existing in the flowchart. So this option block is actually to label your signal processing module, or to give it a title and give it a name. So this top block, you can remove it and give a name to it. Let's say test HITB. So when we will see in the repository, in the folder where this GNU Radio module will be saved as a Python code, we will also see this name which we have defined in the option here. So the Python file will be named by this. And we have the sampling rate by default here, 32,000. So let's just visualize this signal. And to see the waveform, I can use the GUI windows. So now I will use a GUI block. Let's say I use the time sync and the frequency sync. I will connect. So connecting these two blocks is very simple. You just have to click on the output of any block and then click on the input side of the other block. You can also do vice versa. You can click on the input side of this block and then click on the output side of this block, and it will get connected. One important thing to note here is you can see this blue color of this input and output ports on these blocks. So this actually represents the type of data we are processing between these blocks. So if I double click here, you will see the output type mentioned as the complex. You can change it to float, integer, or short. So generally we use complex type signals. In practically, the signals exist in the complex domain. But if you want to change it to some other value, you can change. Let's say I take the float here, click on apply and click on OK. So now it has changed the color to orange. So orange is basically representing the float value here at the input. But now this flow graph has become invalid. Why? Because the output is in the form of complex signal and the input is taking a float value here. So that's how this is like invalid input, and it will show as a red arrow or somewhere in this screen as a red color. You can also see on the top that you cannot actually execute this flow graph. So it is showing that there is a flow graph error. This red button here is showing the flow graph error. So let's just change it back to the original. All right. Now let's see how this signal will look like. So when I press the execute button, which is this green play button here, I press the execute button and then you have to give a name to your file. So let's say I give test HITB. I will save it on the desktop. So a window will pop up because we wanted to visualize our signal using a GUI block. So we use the Qt GUI block. So this is how this signal will look like. You can see that there are two color of the waveform here. One is the blue and the red. So this is what I was talking about when I said the complex and the float values. So when we are talking about the complex signal, it has two parts, real and imaginary part. So this data is representing both of those parts. So let's say I just want to see only one signal. So I'll click on any of these and I should be able to see only one waveform. Now this waveform does not actually look like a sine wave, is it? No. So something is wrong with this sine wave because it doesn't look like a sine wave. And when I'm generating this waveform in a software, it should be like perfect sine wave. But why isn't it so? So something is related with this sampling rate value here. Now let's say I increase the sampling rate to 1 million. And I again execute the flow graph. Now you can see the sine wave actually looks like a sine wave. Yeah, so this is how you can visualize a simple form of signal in both time domain and frequency domain. Right now on your screen, you can see this down part, this part lower is the frequency domain. So if I move the cursor to the top of this signal, I can see that this signal is representing a frequency of 10 kilohertz. All right. So now the important question comes into our mind that what happened when we change the sampling rate and why it was needed to actually change the sampling rate. So to show in a better way that how sampling rate actually works, I will just show you a simple flow graph. So here, what I have done, you can follow up along with me following from this screen. So while I am going to each of the block, so I have taken a simple signal source here. So you can give the sampling rate value as the original, or you can change the sampling rate value to whatever you like. And I have used the frequency of 2 kilohertz right now. Okay, I will explain this throttle block later. You can skip this part for now. So you can just directly connect your signal source to the GUI sync and GUI scope sync. One important thing, you can notice here that I have used the WXGUI FFT sync. So if you click on the options, you will get two options here, Qt GUI and WX GUI if you are you want to work on the GUI console. So if you want to visualize your signal in the GUI, you will get WX and Qt GUI. These are basically the different form of how differently this GUI is being generated. So and I think in the latest version of the GNU radio, there is no WXGUI given there. It's only a QTGUI option there. So in order to select the WXGUI, you need to change your QTGUI to WXGUI, going into the option block. And then after you are done connecting with these blocks, you will just run this flow graph, and then you should be able to see a window like this. So now I can see that the waveform is quite good. It looks like a sine waveform, but I need to select. Okay, if you go to this marker tab here, and if you drop down, there are 4 options. So if you select on the dot large, you will see that the blue waveform is now represented by some series of dots. Let me just turn off this green color line just to, okay. So now these dots are actually representing the samples we have taken out of our original signal. If you will observe here, I have taken a sample rate of 32 kilohertz. Okay, and my original signal is the frequency is 2 kilohertz. So now let's count how many samples we have here. So if we start from the top peak here, you can choose any portion of this waveform, but make sure that you finish at the same point in the next cycle from where you started. So if I take this first point here as the peak point, and if I count it as the sample 1, I'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is the last sample. And if I move one more sample, then it becomes the beginning of another cycle of the sampling. So here I have counted 16 different samples, 16 dots. So these 16 dots are actually representing the number of samples which have been taken from this signal. So our original sampling rate was 32K, but the frequency was 2 kilohertz. So total samples are 16. That is 32 kilo divided by 2 kilo frequency. So if I reduce the samples here, let's say I reduce the samples to 2K, which is basically the frequency of our original signal. Let's see what we are looking at. All right, there is no signal here. Because the sample has reduced to a value of 1, and one sample is not able to represent the signal. If I increase the value of sample, let's say to 8, now the signal is visible, but it no more looks like a sine waveform. Let's check how many samples we have got. So I will again turn off this green signal, going to this channel options, and then I will use the marker option here. I'll use the dot large. So now you can see that there are very few samples shown in the screen here. So if I take the top peak for any cycle, it is the sample number 1, then 2, then 3, and 4. Then again we come back to the another sample here. So now here you can see that these 4 samples are not able to actually represent the signal waveform in its original form, because the samples are so less to actually tell the system that this was the original information. So this blue line is actually connecting through all these sample dots here. So the less the sample, the less it will be similar, or it will be identical to the original waveform. So we need to use a sufficient amount of sampling rate here. So we have the sufficient amount of samples to actually represent the original information which we had. So that's why this sampling rate concept is very important here. Let's switch it back to the original sampling rate. Okay, now let's come to this throttle part here. So this throttle block is actually we use when we want to maintain the sampling rate, as well as we don't want to use all the processing power we have in our laptops. So if we are working with the high sampling rate values and with the complex signal processing modules, so what will happen is when we increase the sampling rate, the processing power will be consumed more, and the laptop or the computer can become slow, and our flow chart will also become slow. So sometimes the computer may also get hanged. So if you are working on Linux system right now, you can actually check how this throttle block affects the processing power in the processing consumption in the computer. You just need to download a small was there a problem with the Zoom connection?
Yeah, I think so. Mine blacked out for a bit, but I think people are coming back. Atit, are you still there now?
Yeah, I'm
Okay.
here. So my signal was crashed just for a while, and now it's connected back. I just wanted
Okay.
to make sure that everyone is able to.
I
Yeah. Okay, I'll switch back to the
think we can
workshop.
continue.
Yeah. So you have to download a small utility which will allow you to see the power consumption of your CPU. You can also use some other software tool. If you are working on Windows, you can actually check when you run this flow graph, how much is your CPU consumption compared to when you are not running the flow graph.
Atit, you haven't shared your screen yet, so we can't see your screen.
Okay. I'm sorry. I think just because of the signal lost in the Zoom. All right. Is it visible now?
Yeah, it's back.
Okay. So I'll just repeat what I was saying. So you need to, there is a small utility which we can use, a small program. So it's called htop. So if you type sudo apt install htop in your Linux terminal and press enter, you should be able to download this very fast because it's very small program. Okay. Now if I type htop -p0, okay, it shows the performance parameters for my machine right now. So I can see the CPU consumption, the memory consumption. All right, so the more a percentage will increase, it can become a problem for my system to work. It may get hanged, the process may stop, and it may be the case that I need to restart the whole program. So let's say I run the program without throttle block. So to disable any block in the GNU radio workspace, you just need to click on the block and press D from your keyboard. So it will disable the block. So if I press D, it will disable this block. But now everything has become red because the only connection was going through the throttle block. So I need to connect again all these blocks together. Okay, now my throttle block is actually dissociated from the original flow graph because I have disabled it. Okay, let's see what the functioning of this flow graph is. All right, so flow graph is now functional, but you can see that without the throttle block, I'm not able to actually, my computer has become slow. It's not giving me the response I want to do. Yeah, so let's check in the program. Okay, if you open the Linux terminal here, it shows that the consumption of processing power here has reached up to critical levels. You can see 99%. Okay. All right, so it can become very disastrous here. Now let's see what will happen if I just close this module. All right, you saw what happened when I was not using the throttle block. The system actually stopped working properly. All right, so I have killed the process now, and now you can see the processing power has reduced back to normal. And I just hope that my laptop is working properly now. Okay, now let's see when we use the throttle block, what will happen. So let's just change the flow graph back to the original by pressing Control Z, and now the flow graph is back to original, and now I will just execute the flow graph again. All right, let's see. You can see there is a significant change in the consumption of processing power when we were using the throttle block and when we were not using the throttle block. So if we compare both, the intelligent option will be to use the throttle block wherever you are facing the sampling rate increase in the signal processing module, or when you deliberately want to operate between so many different type of sample rates. So throttle block is very critical when you are running the GNU radio in the machines which have low processing power. All right, unless you are running on GPU systems, it should be fine with the GPU, especially with this 32,000 sample rate. All right, so just keep in mind whenever you are working with different values of sample rate, so you need to actually understand how much sampling rate you have to use, and don't forget to use these type of small blocks to make things easier for you. So throttle block, and there are some other bunch of blocks which become very handy when we are working with the complex type of flow graphs. Let me just show you now, because when we were talking during the presentation slides, I told you that there is a difference when we analyze the signal in the time domain and when we analyze the signal in the frequency domain. So let me show you how it makes the difference there. I have taken two signal sources here. For the first source, I have taken the frequency of 1 kilohertz, and for the second source, I have taken the frequency of 800 hertz. I'm adding these two signals together and passing them through the throttle block. You already know the reason now why throttle block is important here. And I'm visualizing these signal output in the Qt-GUI sync. So you can find all these blocks by searching here. So if you want to find the Qt-GUI sync, just type Qt or maybe even type GUI. So it will give you all the Qt-GUI widgets here and these blocks. You can just drag and drop any of them. If you are looking for the add block, just type add in the search bar and then it should be here. If you in future want to add more inputs to the same block, you can always change the number of inputs by double clicking on the add block, and you can give any integer value here. So right now we are working with two signals, so I'm taking only two as input. All right. Okay, so this is the two frequencies shown together here. So this is the frequency display here, which you are looking at on your screen right now. And if you are following up on the GNU Radio Live, so you will also be having the same display. So if I move the cursor to the first peak here, I can see that this is a 800 hertz of the frequency. If I move the cursor to the second part, I can see that this is a 1 kilohertz of the frequency. But do you see that there is very little difference here? If this whole spectrum was having different frequencies, it will become very hard to actually distinguish between these two frequencies because these are very close to each other. But still in the frequency domain, we are able to visualize these two peaks. So these two peaks are still differentiable, distinguishable. If you have like good eyes, you can actually see that there are two different peaks for different frequencies. But what will happen when we see in the time domain signal? So I switch back to the time domain display and let's just use only one waveform real part. So in this particular waveform, I cannot actually distinguish where is the 800 hertz and where is the 1 kilohertz. So that's why when we are working with the oscilloscope type of equipment, we actually use the time domain display because there we are dealing with signal which are given in the single input, and these signals are usually not having um, this much complexity of having like too many frequencies together. So when we are working with the radio frequency type of signals, we use the spectrum analyzer type of device because these devices show the analysis. They do the analysis using the frequency display and the frequency domain, and we are able to distinguish each and every component of the frequency into the signal. And also the spectrum analyzers are very sensitive to the frequencies. That's why we use a spectrum analyzer specifically when we are working with the radio frequency type of signals. All right, so this was a very simple example of how time and the frequency domain are different from each other when it comes to the analysis of the signal. Now there is an important concept we use for the signal processing, which is called the Fourier transform, or we generally use the fast Fourier transform. So fast Fourier transform are actually the faster algorithms for discrete Fourier transform. So as I mentioned earlier, that during the process of sampling, we convert an analog signal to the discrete domain, and then we process this discrete samples to whatever process we want to do into the we want to do in our application. To operate on these samples, we use the Fourier transforms. So Fourier transform basically shows you the different components, the frequency components which this signal might have. So FFT is more commonly used during the signal processing because these algorithms are faster than the regular discrete time Fourier transforms, and they play a very important part when we are to process complex signals. So now I will just explain that why we use Fourier transforms, or maybe just in simple way, why we visualize these signals in the frequency domain. So if earlier I used only two signals, but I was not changing the frequencies there. So now I will show you how it will make a difference in the frequency domain. So now in this particular screen, you can see both time domain and the frequency domain waveforms are shown on the screen together. So I will just move the frequency number 1, which is right now the original value was 100. So I will just move this frequency number 1, increase it. So now you can see on the right side that both of the frequency 1 and frequency 2 have become of the same value. And you can see in the time domain display there is only one particular signal we can see. So because both of these signals have only one frequency, so we are seeing only one waveform here. In the frequency domain also, we are seeing only one peak, which is situated at 300 here. All right. Now, if I increase the frequency number 2, so you can see on the right side, the value is getting increased. If I increase the frequency number 2, you can see that there is another peak going away from the original peak. So now we are able to see these two different frequencies separately. If I increase the frequency number 1 further, it will go close to the second frequency. So that's how it makes a huge difference when we observe the signal in the time domain and in the frequency domain. You can see in the time domain, it is still not clear that which part is associated to which frequency, but in the frequency domain, we can see the two distinct frequency peaks here. So you can play with this module further and to learn more about how this frequency display works. For people who are having some doubts that how will they be following up with these modules, so I have created a GitHub repository. The link of that repository I will share with all of you through emails probably, and you can download all these signal processing modules and you can implement them on your laptop or computers, and then you can play around with the signals. Now let me show you a very important concept of low pass filtering. So just like we saw in this signal processing module, that when we have two different frequencies, so it can be the case that we may require to only process or only work on this particular frequency, this lower part of the frequency, or you can say the first peak of the frequency, and we are required to reject the higher frequency here. So in such case, we use something called filters. So we have low pass filters, we have high pass filters, and we have band pass filters as well. So a low pass filter is actually a filter which passes all the low frequency components and it rejects the high frequency components. So how it decides which part to reject and which part to process, it depends on a parameter which is called the cutoff frequency. So every filter has a cutoff frequency. It can have two or multiple cutoff frequencies as well, but a low pass filter, a simple low pass filter, will be having a cutoff frequency as a parameter, and this cutoff frequency will define the window of the low pass filter. So if I take the cutoff frequency as to be 100 kilohertz, so this low pass filter should pass all the frequencies which are below 100 kilohertz and reject all the frequencies which are above 100 kilohertz. So when we have signals, when we have two different frequency components or different frequency of the signals, in general practice, we use the filters to extract out the particular frequency component on which we want to work on. I'll show you how a low pass filter works like. So I have taken a low pass filter module here. You can find it using the search bar. You just have to type low and you will see a low pass filter here. Just drag and drop to the main window here. Also, in order to make it more understandable, I have taken a noise source instead of a signal source. So this noise source is actually representing the Gaussian noise. So it's the general form of noise which we have in nature. And if you might have observed then that when you receive when you are receiving nothing at all in your FM radio receiver, you hear some buzzing sound throughout. So this buzzing sound is actually the noise of the channel which your antenna is actually capturing. So noise also has some value. It's not like valueless. So I have changed the type of noise to float. and the output type to float, and the noise type I have used here is the Gaussian noise. Amplitude should be kept at 1 only. Okay, now I will give the input to this low pass filter. This noise is my input. What I need to define in this low pass filter? I have a decimation part here, which right now I will not change. But in some processing modules, you may require to change this decimation part as well. But right now it's not required. I can also change the gain. So this gain will be actually the gain of the low pass filter and not the gain of your antenna or something, some other hardware. It is actually the gain for this low pass filter. So this filter can have a gain as 1 also, and can have another factor as a gain. So it will amplify the output signal accordingly. The sampling rate can be left as default. So this is the important part of any filter, this cutoff frequency. So I have defined a cutoff frequency of 10 kilohertz here. And I have defined a transition width of 100. So any of the filter which we realize in the uh, uh, in the practical applications are actually not having any sharp cutoff. So when I say that 10 kilohertz is the cutoff frequency, it will never be the case that at 10 kilohertz the frequency, the low pass filter will reject any frequency above the 10 kilohertz. This will fall a little bit uh, ahead of the 10 kilohertz frequency. So it looks like actually this. So you have a cutoff frequency here. Let's say it is the 10 kilohertz, and this cutoff will not be directly falling to this point. Actually, it will fall using a slope like this. In reality, the filters are like this only. Like it's a case with any kind of system which has a cutoff. It's not a sharp cutoff exactly at 10 kilohertz. It will fall down like this. Okay, so we have defined this low pass filter values, and then I'm using the frequency sync as well as the waterfall sync. Here you can find the waterfall sync by typing qtgui, and waterfall should be here. Let me just execute this. Okay, I will just suggest you to neglect the left portion of these diagrams, these flow graphs here. So in the waterfall diagram, you can see there is a blue color and this bright orange color waveform here. In your computer, it can show in different colors, but in general, it is like this only. So this bright color part is actually representing the part of the signal which is being passed through this low pass filter. And this so this will not represent any waveform, any signal beyond the 10 kilohertz frequency. So you can see here is the connection again crashing.
I think the sound was gone for a minute, but I think you're back now.
All right. Okay. So you can see here, these peaks are only limited between the -10 to +10 kilohertz. And you may just neglect this portion on the left. So starting from the 0 to the 10 kilohertz, this positive part of the frequency is actual representation of what we have implemented here. But usually when we represent the signals in the frequency domain, we have a center frequency as the 0, and then we have two negative and the positive sides of the frequency. So this whole extent of negative to positive is actually defining your bandwidth of the operation right now. So this is actually defined by the sample rate which we have in the GNU radio processing module here. So you can see the 32 kilo is the sample rate right now. And you can see here clearly, it is extending from -16 to +16 in the frequency axis here. So actually in total, it becomes the 32 kilo of the bandwidth. Bandwidth is basically the higher end of the frequency subtracted by the lower end of the frequency. So higher frequency minus the lower frequency gives you the amount of bandwidth. So you can see that this signal is not passing anything. This low pass filter is not passing anything beyond the 10 kilohertz frequency here. All right. Now, let's see if we implement this low pass filter on actual signals, we should be able to reject the high frequency signal. So the flow graph will look like this, where I have taken a signal source which is having 1 kilohertz frequency and another signal source having 800 frequency. And I am now multiplying these two signals. So this multiply block will give you two components. One will be the addition of these two frequency components, which are 1 kilohertz and 800. So the addition will be 1.8 kilohertz. And the another component will be the difference of these two frequencies. So it should be 200. Let's see. Okay, so in the upper screen, you can see I have four components, four peaks here. So if I neglect the negative portion of the frequency, so the only thing I need to care about is these two components here. I will just zoom in. You can zoom in by dragging a square box or rectangular box on your window using the mouse. So I have one frequency component here placed at 200, and I have another frequency component here placed at 1.8 kilohertz. So why I have these two frequency components? Because I used a multiply block, and output of the multiply block is always the sum and the difference component of the frequency. But in the lower part of this screen, you can see that I actually have only one component here, which is basically 200 hertz. So if I move the cursor on peak of it, it is 200 hertz, and the 1.8 kilohertz signal component is rejected. Why it gets rejected? Because we are passing the output of the multiply block to a low pass filter, and then this low pass filter is having a cutoff frequency at 500. So anything beyond 500 will get rejected. So the only signal right now we have in the limit of 500 hertz is the 200 hertz component. So if I just zoom into this component, you can see the 200 hertz component is here, but there is no higher frequency component available here because the cutoff of the low pass filter was defined at 500. So that's how you can reject all the unnecessary signals in your signal processing module, and you can start working on the frequency which you want to process in your particular application. But these are very simple flow graphs, and these are very simple process. If you are very new to the signal processing, these may look very difficult for you to understand for now. But the more you will practice on GNU Radio Workspace with all these signal processing blocks, the more knowledge you will get about different signal processing components and the techniques of signal processing. So these are very basic techniques which you must learn, because if you skip all these important concepts, you may not be able to understand more complex type of signal processing modules. Let me just show you something very interesting with the amplitude modulation. So what I have done here I have created an AM transmitter here. Some of the blocks may look very like unknown to you. but all other blocks you have already seen in the previous flow graph. So I have used an audio source here. So this audio source is actually taking input from my microphone from the laptop, and I have used a bunch of intermediate signal processing blocks here. One is the interpolation. So I'm repeating this interpolation and getting it 16 with a factor of 16. So I'm basically stuffing the original sampling rate of the audio source, which is usually the sample rate of 48 kilohertz. And the sampling rate of this audio source is dependent on the type of audio card you have on your computer or your laptop. So in general, these laptops have 48 kilohertz card, and there can be other versions as well. You can see here 44.1 kilohertz is also very popular in some devices, but mostly it is 48 kilohertz. So you need to cross check with your computers or laptops audio card which particular sample rate you may want to use. Usually it's 44.1 or 48 kilohertz. Okay, so now this audio source will take the input from my microphone and pass it to this signal processing block. For amplitude modulation, what I'm doing is I'm adding a signal source here. So this signal source is artificially synthesized using my laptop's computing power, just like I showed you earlier using another signal processing module. And I will multiply this particular signal to this audio source. And for visualization, I'm using a time sink, which is actually not required in this particular flow graph, but yes. So another important component here is this 0MQ sync. So this 0MQ sync, what it does is, it is actually to stream your output data through the digital path in your laptop. So actually what this will do is, this 0MQ is a utility where you can convert your data, whether it is a audio file or it is a image file or it is any kind of other signal you are processing, and you can convert it to a TCP bit stream, and then you should be able to pass it to other TCP path inside your computer, or maybe let's say you want to host this type of signal and you want to access it remotely, then you can transfer this bit stream to IP address, and then this IP address will host this particular signal, and remotely you should be able to access the signal. All right. In the similar way, I have made this receiver. At the input side of the receiver, I have this 0MQ source, and I'm using a translating FIR filter, frequency filter. So I am translating this frequency so as to bring it to a frequency level which I want to operate in the further signal processing part. And similar to the low pass filter, I'm using the band pass filter here, and I'm saving the output of this receiver in a wave file. So I have used this wave file sync here, and I'm saving this as a .wav file to listen to the audio which I have transmitted earlier. So these two signal processing block you can find in the GitHub repository, which I'll share with you in the emails, and you can directly download and start running this program. So I will first execute the receiver, because receiver should be turned on when I am actually transmitting the audio. So I have turned on the receiver. So this is how this receiver will look like. We don't need to actually increase the volume. Let's increase the volume now, because we are not listening it live. Otherwise, it will create a lot of echo on Zoom call. Let me just turn on the transmitter as well. So this transmitter will actually record my speech signal right now live, and it will transfer it. It will transmit it using the TCP IP address TCP address I have given here. And this is actually a virtual address inside my computer itself. And then this same address will work as the source for the receiver. So now I will turn on the, okay, let me just refresh the receiver part, because earlier we were not transmitting. Okay, receiver is on. Let's turn on the transmitter. Let's increase the gain. And now whatever I will speak, it will get recorded into the wave file which is being received by the AM receiver. Okay, so I am saving the received file into my computer. Let's check what I have received. Okay, this is the file which I actually have recorded live. Let's increase the gain. And now whatever I will speak, it will get recorded into the file which is being received by the AM receiver. If it was audible to you all, so that's how this AM transmitter and the receiver work together. So we did not use any kind of hardware right now. We just use the software processing of the GNU radio, and we use the different signal processing modules, a combination of them, to generate a audio signal which was amplitude modulated and was transmitted to the receiver. And on the receiving side, we just received this signal and saved it in the wave file, and then we were able to listen to the signal. So similar type of experiments you can do when you want to understand how this communication thing works between transmitter and receiver. So you don't actually need to have a hardware with you. You can just implement everything in the software. So this is how this GNU radio tool is. This is how powerful this tool is, and it's just the surface of the ocean, which I'm right now telling you in this workshop. So there is a lot more to do in the GNU radio software, and you will learn it eventually if you are like practicing with the signal processing part. Now let me just show you about software-defined radio hardwares. Okay. So if you are not aware about the software-defined radios, these are the hardware devices, the signal processing part of which we can define by software by using a computer or a laptop. So in earlier time, all these signal processing equipment were having everything implemented in the hardware. So we saw all these low pass filters, these multipliers, adders, and everything in the GNU radio. It was implemented using a software tool. But in the older times, all what we have learned on the GNU radio was supposed to be implemented in the form of hardware, which makes the hardware very bulky, and it also adds on to the cost. But in today's time, we just want to reduce the size of technology and do more with the same capability. So that's how we have these software-defined radios. So what happen is they have a basic radio receiver and the other components which are necessary for process the radio frequency signals. But all the other processing part, like the low pass filtering, the amplification, multiplication, modulation, demodulation, all this stuff is controlled by a software tool. That's why these things are called the software defined radios. So this is the general block diagram of a software defined radio, where we have the input antenna and it passes the signal to the ADC. The input ADC will convert this signal from analog to discrete domain, and then this digital signal is now ready to being processed in the computers. So we can have on the other end of the software defined radio signal processing software toolkit installed in a laptop, or we can also pass the same signal to a bigger and bulkier equipment like the spectrum analyzer or the oscilloscope or something like that. We have some bunch of popular software defined radios. So these are the most commonly available software defined radios: Blade RF, Hack RF, and the ATOS Research USRP are the costlier software-defined radios, and the RTL SDR dongle is the cheapest one. But more or less, these work in the same way. The concept is same. The only difference is in the sampling rate and in the bandwidth of the operation. So ATOS USRP has the larger bandwidth, and there are a lot of variants of this particular hardware device. And as you can see, this device has 4 RF ports, and it can work as a transceiver. So it can simultaneously like transmit and receive the signals because it has 4 ports. So you can also implement some multiple input, multiple output type of application on this particular hardware. Compared to the ATOS Research USRP, others are having some less number of ports, and some dongles like RTL SDR are having less sampling rate as well as the lower range of operation. So the maximum range of operation for RTL SDR is only 1.7 gigahertz. So if you are you want to make some application into this range, which is like not going up to the Wi-Fi or Bluetooth range, or the, let's say, the 4 gigahertz, 5 gigahertz range, then you can use the cheaper option like RTL SDR dongles. Otherwise, if you want to go beyond these 4-5 gigahertz range, then you can use the HackRF and the ATOS Research USRP. Line SDR also is another option. So these SDR devices you can buy online, or maybe from some good electronic shops around your place. But in order to like choose the particular type of SDR, you need to understand some basic steps. So when we talk about the radio frequency research or looking into the signals, we should actually follow these steps. So the first step will be that you should choose the range of frequency you want to operate in, or you want to build your application in, and this will depend on what your application is. Also, it will change from region to region, like geographical region to region. So let's say if you want to look into the FM radio signals and you are living in United States, the FM channels may be different from compared to some FM radio channels in the Asian region. So you need to specify the frequency of operation. Then you need to actually go and check the rules and regulations in your country about this frequency region, because every country has regulations over the frequency spectrum. So most of the part of the frequency spectrum is licensed, and it is illegal to operate in that frequency region without having a license to operate into that region. So all these telecom operators, all the ham radio operators, they usually have the license to operate in the particular frequency spectrum, and this license is like costly. So it amounts a cost to access this license, and then you are able to operate, because you will ultimately be interfering with the signals from others. Then you need to select that the particular type of SDR which can cater to this range of frequency of operation of your application. So based on that, you will select which type of device you want to use, whether you can go to a costly device or you can use a cheap device based on your application and your range of frequency. Then you need to prepare your system with all the software tools, because software-defined radio will never work without a good software tool sitting in the machine. So you need to choose the operating system, whether you want to work on the Windows or Linux or Mac OS, and then based on that, you need to choose the software-defined radio tools. So there are a bunch of software-defined radio software tools which are compatible with almost all the commonly available software-defined radio hardwares. And then the most important in the last part is, when you are actually analyzing the signals, please refrain from interfering with the actual communication going on in your environment. You may fall into serious troubles if you don't have the license to operate in that particular frequency band, and if you are creating problem in the communication of others. So I will suggest that please make sure whenever you are using a software-defined radio to transmit some signal, just keep it in a RF shielded chamber or in a constrained environment where you are not actually interfering with the actual real-time communication going on. It may hamper the communication, as well as it may lead you to fall into some legal serious troubles. You may want to avoid that. Okay, let's start with the signals. Hunting. I was talking about the software tools for these software-defined radios. So right now on your screen, you can see the SDR Sharp software. There is a open source software for RTL SDR, HEC-RF, and other bunch of software-defined radios. So this SDR Sharp software is Windows-based. You can install this software going to its website, AirSpy, and there is a process which will guide you to how to install this software-defined radio tool. So now, right now, I have connected a RTL SDR software dongle, RTL SDR hardware dongle. I will just select the RTL SDR dongle here. And then if I click on the play button, I am now receiving the RTL SDR signals. So these are, okay, I should tune into some particular band where you can see some signals. Let me just tune into the FM radio band. So in this software, you see there are a lot of things which this software tells you. So when I have tuned into the FM radio band, then it shows me here in this red strip that this is a FM broadcast. So right now I'm inside a band where this FM broadcast is going on here. So let me just check which are the signals. Okay, sometimes you may see no signals, or maybe just this type of continuous noise. So you may want to go into the settings and then probably increase the gain of the RTL SDR dongle. Okay, so I have increased the gain to an optimal level. Now let's tune in to some frequency and let's see if we are able to. Okay, here we go. So now we have these peaks, which are basically the FM radio signals, FM broadcast signals in my region. Okay, I need to, so there are a bunch of options where you can use the noise cancelling, and you can like improve the quality of the signals. Let's tune into some band which is all right. I'll just I'm turning off the audio so not to interfere with my speech. Okay, so this is how this FM band is looking right now. So if I go to the other band, let's say we go to 390 megahertz. So okay, this band right now you are seeing is basically the public trunk radio system we have. So this band is actually related to the public radio systems, the hand radio systems, and these are the different channels in this particular band. So you should always, before going on to analyze the signals, you should always learn about the particular type of signals you are looking at. So if I talk about these type of signals, I should be able to find out more information on what type of modulation schemes they use, and now what type of signal processing I need to further decode these type of signals. So most of the signals are like not if they are not encrypted, and if they are not using very complex modulation techniques, which usually the signals use these days. So they should be able to easily, like we should be able to listen to them easily on the software defined radio. But the matter of fact that most of the signals are like hidden, and not, you are not able to listen to the actual communication going on. It is because the channel is encrypted, or the decoding is or your software is not able to decode them properly. Let me just show you the mobile GSM band. Okay. So right now, this type of signal is related to the mobile communication. So this is in my region. All the base station antennas and the mobile which are talking to each other, they are operating on these different frequency channels. So this is how we can look into the spectrum. So I started with FM broadcast signals, which I was able to decode easily using this software. So there are a bunch of options for demodulation given on this left panel here. So I use the wideband FM because usually the FM broadcast signal are wideband. And now I'm looking at the mobile radio communication, but I don't have any specific demodulator right now in this software tool so as to listen to this conversation. Also, these days when we talk about 3G and 4G, all the voice data communication is encrypted. So even if you are able to capture the signal, you will not be able to actually listen to any meaningful information. All right. There is one important thing with this software defined, this SDR Sharp software tool. If you go to these options here, it has a SPI server network. So this software comes with this SPI server network utility already. So if you click on this, you will see that it shows you option for different type of IP addresses here. So if you click on these three dots here, it will take you to a portal where you will see all the software defined radios which are right now connected, and they are up and active. You can see on this map, these are all over the world. So basically when you want to remotely, you don't have your hardware and you want to remotely access some software defined radio hardware from someone else who has already installed and set up and hosting it on the internet, you can actually use this utility. This is pretty interesting. All these IP addresses and port numbers here are hosting some sort of SDR communication. So I will just choose the one which are ready and active. So if it shows it is ready, then I should be able to connect to it. So right now I chose one of the device which may be sitting somewhere on the globe, and that particular hardware I'm right now using. So I'm right now not using my own RTL SDR. I'm actually using someone else's RTL SDR or the AirSpy or some other SDR dongle, but I'm using it remotely. So this is basically something called radio over internet kind of thing. All right, so I'm still able to tune in to different frequencies. Let's say I will tune into to the FM band again. Let's say I 90. All right, this is FM broadcast. So it may happen sometimes that the other RTL SDR or the other SDR which you are using remotely may not be having that type of antenna and may not be having the particular type of bandwidth which you want to operate in. So you can always check before actually connecting to any of them. You should check here which type of antenna and which type of bandwidth it has. So right now, this particular SDR is having a Yagi type of VIP antenna, and the name of the SDR is AirSpy High Frequency Plus. The bit resolution is given here, and the center frequency and the maximum range of frequency is also given here. So that's how you can like use remotely someone else's SDR. Also, you can host your own SDR. So you just need to run the spy server utility in the terminal, and then if you are connected to the software defined radio hardware and you are hosting it to some particular static IP address on the internet, then someone else using that IP address can access to this particular software defined radio. Now let me just show you what we can do with the GNU radio and the SDR hardware. Earlier I just demonstrated only the signal processing power of GNU radio, but we can also use a combination of hardware and GNU radio, because sometimes it will not happen that the software tool which we download from internet to use our software defined radio will have all the capabilities which we want to use. So for simple demonstration, I have created this spectrum analyzer, just like I showed you in the SDR chart, but I have used the GNU radio software utility to create this spectrum analyzer. So I'm using a Osmocom source here, which is basically used when you are using a HECRF. So I am connected to HECRF right now, and I have defined a bunch of options here. So I have changed the sample rate to a variable named bandwidth, and I am tuning into the frequency using a variable here, and I am changing the gain of the antenna using the RF gain here, because these gives me this Osmocom source gives me the option to tune and to modify the parameters for the HECRF. I'm using a throttle block in between, and then I'm using a frequency sync and waterfall sync. So let's see how it works on this GNU radio. All right. So you can see it's not very smooth right now, but if your system has more processing power, it will become more smooth and you should be able to see clearly. But it looks somewhat similar to the software tool which we used with the RTL SDR. So you can see I can change the RF gain here. I can also change the frequency using this slider here. Also, if I don't want to like move the slider, I can also give the input by typing the values here, and I can change the bandwidth as well. So I can reduce the sampling rate, I can increase the sampling rate to make my graph more faster or slower. So this is how I can actually look into the spectrum. So let me just show you with what we saw in the so as we saw those 300 to 400 megahertz band in the SDR Sharp software with the RTL SDR, the same channels I'm able to see here. Sometimes you may lose some of the low frequency signal just because you don't have a good quality of antenna and you don't have a good quality of sampling rate. But more or less you should be able to see the signals which are having enough power. So right now I'm using this GNU radio to create a spectrum analyzer. So these type of activities you can do with the GNU radio and the combination of the SDR. You can also listen to the FM signal. You can create a FM receiver using the GNU radio simply and connect a SDR device, and then it should be okay to listen to your favorite FM signal. Okay, so I think we have reached to the end of the presentation, and if there are any questions now, I'm ready to answer. Okay, I think there are a lot of questions in the chat itself. Okay, so the command in the htop is htop space -p space 0. If nobody has answered you yet, so you can, I'll just type the command for you, htop -p space 0. Okay, someone has asked no throttle block in this one. Yeah, it's not always that you require throttle block. So when you are taking care of the sampling rate throughout your signal processing module, let's say in one of the signal processing block, I have a sampling rate of 32 kilohertz, but at the output, I need a sampling rate of 10 kilohertz. So I should use a decimation and interpolator between these two blocks, and I should convert down this 32 kilo sample rate to the 10 kilo sample rate using the decimation and interpolator. So in that particular case, I may not require to use a throttle block because I'm maintaining the ratio of the sampling rate throughout the signal processing block, throughout the signal processing flowchart by using some other modules. So there are a bunch of options for decimation and interpolation values inside the other signal processing blocks as well. Just like we saw in the low pass frequency, low pass filter, we have a decimation option. And similar to that, in the band pass, we have the decimation and interpolation as well. So we can take care of that. But yes, when you are just using one signal processing block and you are directly passing the the output to the sink, then in between you can use a throttle block. All right. Will we get the recordings? I'm sure you will.
Yeah.
After some time when this conference is over, I guess.
Yeah, they'll be on our YouTube channel.
Yeah, and for like, if you want to go to the previous workshop as well, it was more or less same, and there were some different GNU radio examples as well. So you can always like check it on the HITB website. There is a link for YouTube video there. And how do we attack in real life, like offensive techniques to decrypt the encrypted communication? Can you give real life attack scenarios, blog, or any write-up using the analysis of signal processing? Okay, yes. So one simple activity which I can tell you is, if you are having a car at your home, you may probably be having a car key, which is usually wireless. So what you can do is you can create a signal processing module in the GNU radio. So you can attach a software defined radio hardware. Let me just show you how it will look like. So you can just use, let's say, RTL SDR source, and let's say your car key is having a frequency. So you need to check on your car key what is the frequency of operation. So usually if it is just like a simple RC device, it should have a 443 megahertz of the frequency. Okay, I made an error here. It should be E6. All right, so you need to define a frequency here, and then what you can do.
Not visible, Teeth.
Okay, sorry, I think I turned off this. Oh, all right, thank you. Okay, now it's visible. So the simple signal processing module you can create, you can use a RTL SDR source here, and then we can use a file sync. And you may want to add a throttle block as well. Right now, I'm not showing the live demo because I don't have any car or the car key. So you may want to see what you have captured. So you can use a Qt GUI frequency sync, and then you will connect these two, and you can give the location of the file you want to save the file in. So let's say I want to save the file, let's say test RTL dot raw. So your signal should be raw, and it is a complex type of signal. That's fine. Okay. And then if you run this signal processing module, so your hardware should be attached here. So let me just connect the RTL SDR. I'll just show you how it looks like. Obviously, I'm not currently recording a signal. Okay, so this will pop up, this screen will pop up, and when you will press your car key, you will see a significant peak here in this screen. And this information, this signal will get recorded into this raw file, and you can create another signal processing module using the GNU radio. So at that part, what you will do is you will just remove this Osmocom source, and you can use okay, so RTL SDR is not having a transmitter. So if you are using a hack RF or a braid RF or a USRP, then only you will be able to transmit the signal from the GNU radio. So let's say I am using a hack RF, so I'll use Osmocom sync now, and I will replace this file sync to a file source. I'll use a file source, and I'll give the location of my recorded file signal, which was, where was it? It was on desktop. Yeah, test.rtl.raw. So I'll give the location of the file. I will connect this to the Osmocom sync. And when I will transmit this signal, your car should get, car door should get open. If it is a simple car key fob, like the older one. Right now, even the car key fobs are having the encryption. So that's why I like to make them more secure and to counter as a countermeasure for this type of attack. Also, if you look at the more practical scenario, you might have heard of the IMSI catchers and people attacking the GSM communication of other people. So there are a bunch of write-ups and blogs and projects which are given for this particular purpose. So GRGSM is one of the project which you can use to check what can we do with the software-defined radio and the GNU radio to actually intercept the GSM communication. And if it is not encrypted like the 2G communication, you can actually listen to the voice of people. But please, as I mentioned earlier, because these things create legal issues, so don't do it with an intention to actually interrupt the communication of other people, and do it for the experiment purpose only. So you need to set up in between two computers, and then only you should be able to do it in a lab environment only. All right. Any other kind of question related to any of the topic of this workshop? I think we are already over the time.
Yeah, we're over the time, and I don't see any questions coming in. So I would like to thank you, Atit, for your workshop. It was really interesting to see all of your techniques. And I would like everybody that was here for attending. So please remember that you can continue our discussion in the Discord channel if you want. I'll post the link in the chat. And you can also join our Brella platform, which helps you in networking and getting to meet people and gives you the opportunity to go to our villages and exhibitions. So I'll post the link as well in the chat, and I hope to see you there and have a great event. Thank you very much.
And just before you close the session, just want to inform everyone that we have on the Brella, we have the RF village as well. So I will be active on that till tomorrow, or maybe even further. So any kind of topic you want to discuss, you can just open the chat box and you can go there and type in your questions or your doubt, and probably I will be able to answer all of your doubts there. So there you can have discussions among yourselves as well. I think there can be someone who is working in some interesting technology using the software-defined radio. So we can use that platform as well. So please just make good use of these all these facilities and platform provided by the HITB this time. And yeah, thank you all.
Have a great evening. Bye-bye.